Okay, so you have to do the introduction, then we can just.
Good afternoon, folks. Here we have Professor Sandeep Kundu. Is a professor in electrical and computer engineering at University of Massachusetts. Recently, he has served as a program director at the National Science Foundation. Kundu begins his career at IBM Research as a research staff member. Then he worked at Intel Corporation as a principal engineer before joining US as a professor in 2005. He has published nearly 300 research papers in VLSI design and test, holds several key patents, including ultra-drowsy sleep mode and process, and is given more than dozens of tutorials at various conferences. So welcome, Sandeep. Welcome all. We'll take a short break at sharp 3 o'clock for 15 minutes. So before that, we'll take a couple of questions. The presentation till done for that time. Okay, thank you. Floor is yours.
Okay. So can you guys hear me? It's good? Okay. So before I start making any presentation, I like to get an idea about the audience. So is any of you working with any sort of AI hardware? Okay. And specifically, do you work on the hardware-software interface or in the core design with algorithms? Yeah, great. So, so that's about almost maybe 15% of the room, and then looks like 85% of the room hasn't really done anything, and so that's kind of sets the audience level for us. What I'd like to do is, without further ado, like to get started. Here's the overview of the presentation. I'd like to spend some time in introduction and organization, and then talk about the basics of convolutional neural network. Yeah, and then the purpose of doing that is to understand the algorithm and where the complexity issues are. And then we look at the kernel functions that we use, and specifically the things that we are trying to accelerate in the hardware. We don't try to accelerate every function in the machine learning algorithm. That would be a fool's errand because it's not going to give you that much performance benefit, but it's going to cost you a lot in terms of hardware. So specifically, if something takes like 90% of your computation and something else takes 10% of your computation, if you can speed up 90% of the computation, then a lot of times you have already achieved your performance goals. You don't need to speed up that 10% because the cost that you'll put in, it may not be justified in terms of power and the transistor count, et cetera, et cetera. So that's why we try to only accelerate the kernel functions, the functions that you invoke repeatedly and where acceleration is going to give you benefit at a reasonable cost. And today, almost everybody is trying to accelerate. Okay, so if you look at companies like, at Intel, for example, you have your approach for acceleration, which is through modifications to the Intel instruction set architecture. In 2022, Intel introduced the Sapphire Lake processor, which comes with new instructions called AMX instruction. And those instructions are specifically designed to speed up the tensor operations that happens in processors. And then NVIDIA has its own ways of accelerating. Google has its own way of accelerating. And even the memory companies are doing all sorts of acceleration. So the question is, where is it appropriate, and what are the cost-benefit trade-off, and what is the application space, what is the application domain? So all of that comes into play. So for example, Tesla builds its own hardware for accelerating machine learning for the self-driving system. And so you could ask, why is Tesla building its own hardware? And why aren't they using Intel processor? Or why aren't they using NVIDIA processor or something else? Because clearly it's an expensive proposition for them to be designing hardware. So we have to understand what are the constraints, what are the concerns, and what are the applications that actually dictate the choices that people make. So these choices are not made out in vacuum. They happen under various constraints, and so we just need to understand the trade-off that's involved there. I will then talk about basic CPU architecture and parallel processing. It's still a core of acceleration technique, even though it's something that sounds like people have been doing for ages. And yes, people have been doing it for ages, but it's still very important to get that done because that's your first line of opportunity in accelerating ML. And then we will look at the specific hardware components. I will look at TPU, Google TPU as a case study as to how they made the design choices in the design of the TPU chip. And then we'll talk about metrics and architectural trade-offs. I probably would not have time to cover everything that I want to cover. So there'll be times when I'll be just running through the slides. Bear with me, but there's a lot to talk about. I will just skip this about myself and jump directly into where it all began. So it's a brief history of where it all began. And there was a physician in Spain, Santiago Ramon y Cajal, and he started looking at brain because they had just discovered this new technology called staining. If you take a slice of the brain of any animal or human, and if you look at it under a microscope, you're probably not going to see much because all the tissues look pretty much the same color and same everything. But by then, people discovered that you can stain the tissue with different kinds of compounds, specifically some silver-based compound, which actually makes the differentiation between various tissue strands possible. So Ramon y Cajal, he started looking at that, and he studied various animal brains, rabbit brains, in particular, he spent a lot of time studying. And he found that all the animals and also the humans, they shared the same brain structure. And so that was the first thing that he found. The second thing that he found is that the brain is made up of neurons, and these neurons are organized in very specific ways. The three specific ways that he looked at, they're organized, are space, matter, and latency. So he wrote in Spanish that all brain structures follow three rules. The first rule is that the neuron has to pack densely. So you cannot have an architecture when you're doing hardware where one transistor sits here, another transistor sits here. You try to make an interconnect between the two, you're going to have large interconnection delay, and you're going to have large amount of power dissipation in the interconnect. Exactly same principle applies in the brain. Everything has to be packed in a 3D structure in the densest possible way. And he wondered about the brain structure, that how everything fit perfectly in the 3D space, all the neurons and all the connections. Then, in order to fit things in the perfect way, he also found that they follow the law of matter. So, for example, if you're building bricks, if all the bricks had different height, then it will be very difficult to lay out your bricks and make a dense structure, right? So the bricks all have to be the same height so that they all pack densely. And what he observed is, with respect to the neurons, they also follow that property. And when you go into hardware design, we try to use exactly the same property, that when you do the basic physical tiling in the hardware, we'll have to fit them exactly, whether you're doing 2D or 3D structure, so that you have the densest organization possible. And the third thing he found is that everything in brain is optimized for latency. So this is something, those are his three rules in Spanish. And he found that the conduction time in the brain is very optimal. why do you think eye is located here and not here? Because if the human eye was located here, there's going to be conduction time for the signal going from the eye to the brain. It's going to add to the latency. In fact, if eye is a fantastic structure because the optical nerve that connects to the brain is actually very different from all the other nerves that humans have. The optical nerve is actually an extension of the brain. When the signal travels to the brain, it's already doing processing on the way. So it's not like the signal is carried to the brain and the processing is done there. Processing begins right after the optical nerve starts in the eye. He also found that in order for all of these things to happen, for the performance to happen, everything had to be unidirectional, because if the signal flow was bidirectional, the time that it will take in switching, you could not make the brain work as fast as it needs to work. So for example, if you're running away from a predator for an animal or human, then you first have to sense that there is a danger, and then you'll have to act. If there's a delay in the sense time, you will not survive as a species. So that's a fundamental requirement, that you must adapt to the physical world and respond in real time. These lessons all hold true when you do hardware design for machine learning. I'll skip through, maybe I'll just talk about the structure of neuron. A neuron basically has axons. It's a cell that has these connections, and one type of connection is called axon. It's the transmitting part of the neuron. It's like the output of the neuron. It has the dendrites, which is the input to the neuron. And these neurons connect to each other through these little things here. These are called spines. And so that's the connection between the input and the output. Now, typically, the neurons, for a baby, human baby, it has about 15,000 connections per neuron. When you do any kind of machine learning algorithm today, our algorithms don't have 15,000 connections. If they did, we'll not be able to design circuits for it. Because if a device had to drive 15,000 outputs and have 15,000 inputs, forget it. It's not going to happen. So the human brain, as an adult, it has about, on an average, 7,500 connections per neuron. So when you're born as a baby, we start out with 15,000 connections. Then by the age of 2, we are down to 10,000 connections. And then we are down to about 7,500 connections as adult. This process is called pruning. And there is something very similar happens in machine learning algorithms when you do the optimization. We also prune the network in order to optimize for hardware mapping and in order to get performance. So the humans do it, and we basically, as a child, we learn things very quickly, and we have all these connections to program. But then we figure out that not all that information is relevant, and so we begin to filter out things. We lose these connections. So inspired by the neuron, the first circuit which was designed, it's a computation model, it's actually not a circuit, was in 1943. The structure of the brain was understood in 1899, so give or take about 44 years after that. The first computation model came on how to use the neuronal structure in order to do the computation. And so the idea behind Perceptron was that you have a bunch of inputs and you have an output, and these inputs are binary. They can be zeros and ones. They can be 0 or 1. And so what you do is you produce an output, and the output is such that if each input multiplied by some kind of a weight, and when you sum them together, if they're above 0, then the output is 1, and otherwise it's 0. The output is 0. So that's a binary input, binary output. And that was the first circuit that came about in 1943. What can you do with perceptrons? It turns out you can do a lot. You can take perceptrons and you can build AND gates. Here's an example. For example, if you choose weight as 1 and 1, and if this is 1 and this is 1, then together they contribute 2. You subtract 1.5, this is a bias, minus 1.5, it's greater than 0, so the output is going to be 1. If you do a combination, different combination, so you will find that if you do a different combination, then if you put 0, for example, here, 0 times 1 is 0, and 1 times 1 is 1. When you add them together, you'll get a 1. Subtract 1.5, and output is minus 0.5, and that corresponds to 0 output in the perceptron. So you could design an AND gate, you could design an OR gate, you could design an inverter, and we could ask a lot of questions, but for the sake of time, I'll just skip through. I'll just quickly run through how this field developed after that. So 1943 was the first circuit model with Neuron. And then in 1950, Turing defined what's machine intelligence and what is intelligence in general. So there's a Turing test, and the Turing test says that if two agents are interacting, one of them is a machine and the other one is a human. And if you're interacting with both of them without knowing who's human and who's machine, if you cannot distinguish between the two, then the machine is intelligent. But if you can distinguish between the two, then the machine is not intelligent. So that's Turing test. Okay. And in 1952, the word machine learning was coined. So this was machine intelligence, and this is machine learning. And this was done by Arthur Samuel, and he was a professor at Stanford. And then 1957 was the first artificial neural network, or ANN, and that was then. Then not much really happened between 1960s and 70s, except that some incremental improvement in algorithm design and some understanding of how we could build division, et cetera, et cetera. And then 1970s is largely called AI winter, when the whole field was not developing, people were not interested. 1982 was John Hopfield. He created the Hopfield network, and this is the beginning of the spiking neural network. And then really the activity picked up in 1986 when Jeff Hinton and Rumelhart, they came up with this algorithm called backpropagation algorithm. Unfortunately, I wouldn't have time to go through the backpropagation algorithm. It is the backbone of how the machine learning models are created, how the training process happens. And I guess some of you already know how it works, but that's the core thing that actually made all of this possible. 1988 was a big thing because Jan LeCun, who was a student of Hinton was teaching at Toronto, and LeCun was a student of Hinton. He, for the US Postal Service, he created this handwritten recognition system where a machine could read the zip code when you write down this, and with a sorter, they'll be able to push the letters one way or the other, which will go into different bins, and that will allow them to sort the mails. So, and at that time, mind you, that in 1988, emails were still not very popular. When I was a PhD student, for example, only about 7 or 8 nodes were connected in the US, and the emails were carried by courier service. The university where I studied, when we sent an email to someone, then it was written onto a floppy drive, and the floppy drive traveled by a courier service like FedEx. It went to the other end, and things got uploaded. So, postal service was a thing those days, and there's a high volume of letters. So, postal service, contracted him to do the handwriting recognition, and that was the beginning of the thing known as LANET. And then in the game playing world, 1997 was a big event. IBM Deep Blue won the chess against Kasparov, so which was big event. And then around this time, the boosting algorithm came, and another big event happened in 2009 when Fei Li, who's now a faculty at Stanford, she was doing her PhD under Fehlbaum, And they realized that there was not enough data in the world to train machine learning algorithm, which is one reason why it was not going anywhere. So they decided to first create a big database, and which is today known as Imagenet. And it's large, annotated, and categorized visual database. And this is what people use today to train their machine learning algorithms, at least for those who don't have access to private data like Google and others. And so it became the training ground, and it was a big thing. And so on and so forth. So once the ImageNet was, the database was created of these images, then they started a competition who could classify those images better. And the AlexNet came out in 2012, and that did most of the foundations of today's machine learning algorithm, such as using ReLU as a function, such as using parallelization. He was the first one to use GPU for training network, and many of the concepts that we are using today, it started with AlexNet. Microsoft improved on the AlexNet, and by 2015 it was ResNet, and then 2016 it was the AlphaGo by DeepMind, which basically revolutionized. So that's a brief history of machine learning. We need to understand some of these histories. Sometimes go back to see how the field developed and why they developed the way it did. I will next talk about the convolutional neural network. I'm skipping over a whole bunch of context in between, but this is something which is necessary to understand the kernel function that you use in the machine learning algorithm today. And the kernel function that you use at the machine learning today is convolution. And that's the convolution is the basic thing in the convolutional neural network. So I'd like to spend some time. And many of the slides I've attributed because I've taken from various sources. Most of them come from either Stanford, where a lot of the early work was done, and then from other sources as well. And so they're acknowledged at the bottom. So here is a very popular data set for the students to use. In any class that teaches machine learning, which is the CIFAR-10 dataset. And in CIFAR-10 dataset, you have a set of pictures, and these pictures are labeled. They're airplane, so these are all airplanes, automobiles, bird, cat, deer, et cetera, et cetera. So the idea is that given these images of all these images of the airplane and all these images of the automobile, you try to train a network which then, once it is trained, if you give an image which belongs to one of those 10 classes and ask which one it is, it should be able to give you the correct answer. Okay. So in the CIFAR-10 dataset, there are 10 labels. These things are labels. And in this case, we have associated names, but this could be numbers. This could be class 1, class 2, and this could be like class 10, okay? And in this particular case, in the CIFAR-10, they have images that are 32 pixels by 32 pixels. So, and each pixel can be R, G, or B, or 3 planes. So the amount of the data that you have per picture is 32 times 32 times 3, okay? And which is 1072. So that's how many pieces of data that you have. And each piece of data is about a byte, because we represent the color between 0 and 255 for each one of the R, G, and B. So this is how many bytes of data that you have in each picture. The problem becomes that how can I train a network so that it's able to classify those images? Now, in the CIFAR-10 dataset, there are 50,000 training images, and there are 10,000 test images. So you train the model with 50,000 images, and you test it using 10,000 images, and you try to figure out what is the accuracy of the model. So if it's able to classify large number of them, you could just say that my accuracy is 95% or 96%, or whatever. It's almost never going to be 100%, but you try to do as good as you can do with your model. So basically what you have once you have trained a model is you have an input image and you run it through the machine learning model, and it's going to produce numbers, and it's going to produce a vector of numbers, and there's going to be 10 of them, and each of them will have a score. And so at the end, you'll say that this score may be 5, this score may be 10, this score may be 15. Because 15 is the highest score, after you've gone through the image, you say, I think it is this, and it's not that or that. Okay, so that's how it's going to work. So how are you going to compute that score? So let's look at how the model is going to do the computation. And so you have an image, which is 32 by 32 by 3. It has a width of 32, height of 32, and a depth of 3, or RGB plane. And then you apply something called a filter. And this filter, in this case, we show is 5 by 5 by 3. But more recently, this was the thing that AlexNet used most, the common size. But more recently, like with Google MobileNet, they're using filters that are mostly 3 by 3. They're not 5 by 5. And so in this dimension, it's 5. This is 5, and the depth is 3. So what you do is, in the convolution operation, you apply the filter on the image. So you place this filter on the image somewhere. And so let's just say that right now we have put it here. And then for each one of those elements, we perform a dot product. So the way it works is, on the image, wherever you are placed, you have 5 by 5 by 3. So let's take the part of the image. It's not the whole image. It's just part of the image, which is 5 by 5 by 3. And so I have 5 in width, 5 in height, and 5 in 3. If I serialize that as a vector, the vector has a dimension of 75. Okay, so I get 75 numbers here. And my filter has the same size, which is 75. And then I will take this element in the image with that element in the filter, this element in the image with that element in the filter, multiply them all together, and add them up. And when I add them up, then I also add a term which is called bias. The bias is fixed, and it's basically, I apply it to do a fundamental shift operation of these numbers, and so that we end up with a score. Okay. Now, the way convolution works is, first we place the box here, and we produce a map here, and then we slide the box by one more position and compute this number, and then slide the box by another position and compute the next number, and so on and so forth. So you could slide the box in the X direction, you could slide the filter in the Y direction, and you'll be computing an output which is known as the activation map. Now, because this size was 5, once you place it in this corner, then you have a room to slide by 32 minus 5, which is 27. And the very first time you put it, it's 1. So in this dimension, the output is going to be 28. And when we slide the box this way, in this dimension, the output is going to be 28. So when you have done that, we have created an output activation map. So that's your basic convolution algorithm. And when you do that, if you did that with one filter, we'll get one activation map. Then if you do another filter, we'll get a second activation map. And if you do a third filter, we'll get a third activation map. So what we are doing is we are stacking the number of activation maps depending on how many filters we are applying. And eventually, we have, when you apply n number of filters, we'll end up with a depth of n in the activation map. Now, in this particular case, suppose we applied 6 filters, we'll get 6 different activation maps, and that's how we have done the convolution process. Now, once we have done this convolution process, then what you're doing is we are given an input image. By applying a set of filters, we produced an output activation map. And then on the activation map, we apply something known as an activation function. This activation function, if you remember in the Perceptron, which was designed in 1943, the activation map was that you take all these inputs, and if they're over a threshold, then we output a 1, and if they're below a threshold, we output a 0. So if I plot that, if I take my total, and if my threshold was here, and so what I'm saying is if the output was less than threshold, it was 0, and output was more than the threshold, the output was 1. So this is, in this axis, I have input, and in this axis, I have the output. What function is this? It's a step function. Analog approximation of the step function is a sigmoid function. And a sigmoid function, it looks something like this: 1 divided by 1 plus e to the power minus x. And so when you do this, then it's centered around 0. And if you go like something like beyond 5, this is already 1, and beyond -5, it's already 0. And somewhere here, it looks something like this. And you can also make that a function even more steep by adding multiplying x with a constant k. And sigmoid function will get even steeper. It'll look more like a step function as you keep increasing the value of k. So one of the things that people did early on was that we produced this activation map by doing convolution, and then we are going to apply on each one of those output maps that you produce something like an nonlinear activation function, which is like the perceptron, which is like the sigmoid function. So the sigmoid function was used for a long time, and it looks something like this. And later on, the sigmoid function has this property that it goes from 0 to 1. Tan H has some superior property than sigmoid. It's a hyperbolic tan function, is that it goes from -1 to +1. And so because it produces both negative numbers and positive numbers, then when you do this convolution operation, then the output of the convolution is going to be zero-centered probabilistically, which is better than having it non-zero centered. And so tan H got brief popularity because of that. But all of these activation functions, when they're applied in practice, they had certain limitations. And I'm not going to go into those limitations, but basically the problem was with the back propagation. It actually did not produce, the learning rate was very low for these kinds of functions. So in AlexNet, Alex Krzyzewski, who was also a PhD student of Jeffrey Hinton in 2012, he used this function called ReLU function, which is rectified linear unit, where the function is 0 here when the summation of after doing the convolution, when the output value is negative, it's here, and then if it's greater than 0, then y equal to x. That's your rectified linear unit. So this is the nonlinear function which is applied. This is the most commonly used function today in at least computer vision. But there are other functions that people have used or continue to use. So convolution layer is basically a sequence of convolution layers interspersed with activation function. So we just seen what an activation function is. It's something that takes the output of the convolution process and then does a nonlinear mapping. Okay. The convolution process itself is basically a dot product computation between the filter and a small part of the image. So why does it work? And we need to have some sort of an intuitive interpretation or explanation. And for that, you can go back to something that you have done since high school days. So suppose I have a vector, and the vector looks something like this. And this could be in a two-dimensional space, let's just say, that I have a vector that looks like this. And I have another vector that looks like that. And now these two are, let's say, some representations of features, and I'll explain what a feature is. So during the convolution process, what you're doing is you're taking the filter, and the filter, if it was 5 by 5 by 3, I'm vectorizing it, and the vector has a 75 elements, and my image also has 75 elements. But I'm just saying that for the time being, let's just assume that my image has only 2 elements and my filter has only 2 elements. Okay. Now, if my image has only 2 elements and my filter has 2 elements, and suppose this is my image. Okay. If I take the dot product between these two and dot product between those two, what will happen? What is the dot product? In dot product, we take a perpendicular, and then this is the dot product, right? And here we are taking a perpendicular, and this is the dot product. So in this case, when I take the dot product, and if they're all unit vectors, let's just say, so these vectors are all, so this has a length of 1, this is a length of 1, this is a length of 1. Then my image, is it closer to this or closer to that? The first one, right? Because when I take the dot product, it's going to give me that feature. So what you're doing is when you're doing a convolution process and computing a dot product, the filter is really a set of features. And we are saying that does this image have that feature? So for example, if you're trying to recognize a human face will have an eye, 2 eyes, let's just say. I'm scanning this image. Suppose I have a filter that looks like an eye, okay? So all the pixel values inside the filter that looks like an eye. I scan that filter throughout, and then I say, do I see an eye? And then sure enough, those are represented as dot products and values. And I might see a value of -5 here, -7 here, and then here I might see 10, and here I might see 12, and then here again I can see a bunch of negative values. So from there I could say that I found an eye here and I found an eye there, okay? But that's still not a human face, right? Because my filter was an eye, and that's still not a human face. Then I can do the same thing, filter maybe a mouth, and I say, do I see a mouth here? And then say, okay, I found some, dot product is giving me higher scores here. So finding a filter is like finding those features, okay? And now what happens is if you look at, CFR10, if you look at a network like a car, and you run it through this algorithm, and then you say that, what are they finding? So on the first layer, the filters looks like this. If you actually train a neural network, which is like finding the values of the elements in the filter, and then showing it in a picture, then for a car, it looks something like this. The first filter will look like this. And so you take that filter, you scan it, and say that, what am I seeing? And you have a score. So when you do that first level, maybe you're just trying to find the wheels, and you're trying to find the headlights. And so in the first layer, what you do is you find those scores, which is telling you where the headlights are and where the wheels are. And in the second layer, you do exactly the same thing, another layer of convolution on the output of the first layer, and then you're finding the mid-level features. And then you keep doing that, you'll find the high-level features. So in Google MobileNet, there may be like 55 layers. So in 55 layers, you go through that, and you keep finding those features, and eventually you try to find a match, okay? Originally, when AlexNet came out, it had, 12 layers, and then ResNet came out from Microsoft in 2015. It had 16 layers. Today, Microsoft ResNet has 152 layers, and so those are, the quote-unquote improvements that has happened. But fundamentally, the algorithm has remained the same. Okay, and if you look at this is image processing, but if you look at something like text processing, it's again the same sort of construct, except in that case, the input is your words instead of being pixels. And the biggest innovation that happened there was something like when you do the convolution and you have this convolution net, is taking the output from one layer and feeding it forward. And that's called the attention layer, which is, you might have heard GPT, which is also based on attention layer. But what really fundamentally has changed is the convolution has remained the same. We have added all this slightly extra tweaks. The model size has become incredibly big. The GPT-3 has 5 million parameters or something like that. It's just incredibly big. And I may be quoting the number wrong, but you can check that up in Google. But the models are very big. So now I'll talk about complexity, talk about kernel function, and talk about acceleration. So we just understood what is the basic convolution process. And let's think about complexity. So suppose my image is 7 by 7, and I put a 3 by 3 filter. I first put the filter here, and then I'm going to shift and put the filter there. Then I'm going to shift it all the way. And so I'm going to when I shift it like this, my output, starting with a 7 by 7 input, I'm going to produce a 5 by 5 output. Okay. Now for each output, so how many outputs I'm producing? 25. For each output, how much computation am I doing? I'm doing a dot product of 9 elements. Okay. And so multiplied by 9. And I'm also adding a bias, so 10. And this 9 elements may have a depth. And when you at the first layer, the depth is 3. But in the intermediate layers, the depth might be the number of filters, and the number of filters can be very large. The number of filters can be 50, 60, 100 filters, because each filter, as I said, could be an eye, eyebrow, ear. And so it's like, you're applying a very large number of filters, trying to find the match. So then multiplied by your depth, or the number of filters. So that's kind of the order of complexity in doing the convolution operation. So here's some more details. I'm just going to skip over the details. So you basically got the idea about the complexity. Now, in this whole model computation process, the convolution operation takes 85 to 90% of the computation, and remaining 10% of the computation are, finding the nonlinear values, which is the activation map, doing the normalization, because after each of those steps, the inputs are normalized, and because that improves the accuracy, and so including normalization, including nonlinear activation, and including Softmax layer, the very last layer of computation, which I didn't describe. I'm going to describe that. It's about 10% of the computation. So this is if you want to accelerate something, this is what you want to accelerate. Okay. If you have more resource, you would of course accelerate the other things if you could spend more resource. But if you have some resource to accelerate, that's the first line that you're going to accelerate. Okay. So how are this convolutional neural networks trained? So each filter has a weight and bias. And problem is that during the training process, you have to find the weights, and you have to find the filters. So that's what you have to find, like, what is contained in each one of those filters. And you do that by minimizing a loss function. And how is the loss function calculated? So there are many loss functions, but I'll just stick with the one which mostly everyone is using, which is the Softmax loss function. So Softmax function is also known as multinomial logistic regression. It's a fancy name. But let's just say that I have an input image, and I just ran through, I just ran through this my convolutional neural network process, and at the end, when I'm done with the convolution, I computed some scores. Okay, when I took the dot product, I computed some scores, and in this particular case, let's just say that I've computed all the scores, and then I've done something like a linear combination of all the scores, which is typically known as the fully connected layer, and got my final scores. what is the likelihood that this is a cat, what is the likelihood this is a car, and what is the likelihood this is a frog. There are some steps in between which I'm skipping because this is not an algorithms lecture. I want to get to the hardware part. And so when you do that, the first thing we do is we take the scores and then we exponentiate them. And so in the exponentiation process, we just raise that 3.2 as e to the power 3.2 and 5.1 as e to the power 5.1. After I've gone through this exponentiation, we get these scores. And then we normalize it. So basically, in the normalization process, we add these numbers together, and then you take the ratio. And so everything is now scaled such that when you add them up, it'll have a value 1. And then we just say that I input an image called cat, and my score for cat was 0.13, whereas my score for car was 0.87, and whereas the score for frog was 0.0. So am I classifying my image correctly or not? I'm not classifying my image correctly. So what in the ideal world I'd like to do is I'd like this score to be as close to 1 as possible. And all these scores then in the process will be going down. So this is my loss function. The loss function I just calculated mathematically. And then based on this loss function, I'll go and change these weights such that 1 pixel at a time, such that if I change those weight values, I'm trying to raise the score to a 1 or as close to a 1 as possible. And this is done through an iterative process. This is done with an iterative process. So we start with random values for a filter. We just populate the filter with random values. We compute a loss function. And then after that, we compute delta L over delta W. So where delta W is each element, delta Wi. So if I change this by a small amount, how much will my loss value change? I calculate that. And based on that, whoever has the highest gradient, that's the pixel value I'm going to change. And I iterate through that process. And this is basically known as gradient descent algorithm. And many of you might have encountered this. It applies to many problems, including my former field when I worked on electronic design automation. I used gradient descent a lot. So the gradient is a vector of partial derivatives, and the gradient has property that the slope in any direction is the dot product of the direction with the gradient, and we use that property to find the values of those elements in the filter, which will give you the best optimization. Okay, so we are done with the kernel function. What time is it? How in terms of time from the start? 1 hour. So I'm on track. No, actually faster than track. Fantastic. And so we'll go into kernel functions. And you guys can feel free to stop me and ask questions because every speaker likes to be interactive. Let's do the complexity analysis. So what does it look like? So we have a number of filters. So for filter equal to 0 through number of filters, we have a number of channels. That initially the channels are RGB, but then subsequent layers, whatever was the number of filters in the previous layer, that's the number of channels. And so for number of channels, and we are computing the convolution output, which is for output height and for the output width. And this is the filter height, and this is the filter width, and this is the dot product computation. So that's your basic mathematical loop that you have in the convolution function. And so order of the computation of convolution is number of filters times number of input channels times number of output height times number of output width times kernel height times kernel width. This is a calculation that we just did, okay? And so as you can see that these loops, they just blow up. And I also said that in AlexNet, he was generously using big filters. Of course, big filters will give you, a better quality result. But then when you went into mobile net, for example, in Google, they're using really small filters. And why? because in this equation, you already have very large number here to deal with. And then if you increase the filter size, can you imagine what will happen to the order of computation? If you can go from 3 by 3 filter to 7 by 7 filter, and the number has gone from 9 to 49. So you just blew up your computation by 5-fold, okay? And your training time is now going to be like, 10-fold. And so it would be a ridiculously large number. So that's what the kernel function is telling you. And this is what we are trying to accelerate using hardware. So we take this kernel function of this convolution. We would like to use hardware to speed this up. And how can I do that? What are the trade-offs? And why is Google doing one way and why is Intel doing another way? Speeding up kernels, what do you want to do? We want to reduce the order of computation. So one way to reduce the order of computation is choose hyperparameters wisely. What are hyperparameters? These are the parameters which are not found during the optimization process, but which are defined by the users. So some of the hyperparameters are number of layers. How many layers of convolutional network I'm going to have. So for example, ResNet 16 had 16 layers from Microsoft. ResNet today has 152 layers, okay? And so so choose wisely. If you don't need to use that many layers, you really need to stick with fewest number of layers. You want to do model size reduction. How can I do model size reduction so that I reduce the number of computations? You can use model size reduction, and I'll cover that going forward in the lecture. But sometimes model size reduction is totally incompatible with hardware acceleration. And so we'll have to think about how I'm going to run my model. We have to think about parallelization. And the two common ways of parallelization. One is data parallelization, which is doing vector operations. So at the end of the day, we just want to do vector computation as fast as possible. Because at the core of that convolution operation is a dot product, and we want to speed up that dot product computation as much as possible. And so, for example, the latest thing that Intel is doing in Sapphire Rapids is they have a multiplication unit for acceleration, which can take a vector which is 16 by 64 and multiply them all in one shot. And so that's AMX. It's tremendous amount of hardware, tremendous amount of power, but it speeds things up. In case of NVIDIA, they're doing similar things. They have a number of chips and they do vector operations of different width. In case of Google TPU, the first TPU they did 256 by 256 vector multiplication in hardware. And so everybody is doing some part of this vector operation they want to speed up, and somebody is choosing to speed up a large part of the vector in hardware, and somebody is choosing a small part of the vector in hardware. What are the trade-offs? If you do TPU, for example, you have very large area, you have very large power consumption. On the other end, if you try to do, something like the traditional, the Qualcomm NPU approach, then you take a much smaller vector in terms of parallelization, because you're trying to also fit within the power envelope, which for the mobile process has been stuck at 5 watts for a long time because your mobile battery capacity has not been increasing. And so you really cannot spend any more power than 5 watts during peak computation in mobile processors. Okay, so that's, you do this. You also do parallelization, like I talked about data parallelization, which is vector, and task parallelization, which is horizontal scaling. And so in horizontal scaling, this is really the power of GPU, because a GPU has very large number of processing elements, and all of those processing elements can compute in parallel. So in the convolution, we saw that the big loops, and if I can take various parts of the loop and then parallelize them across number of processing elements, I'm going to get speed up, which is what has been selling the GPUs for a while now, except that everybody else is beginning to catch up with their things. And of course, GPUs are also tremendously expensive in terms of power. But GPU is not the only way to do task parallelization. If we had thousands of CPUs, we could also parallelize tasks, except that the cost of communication between these tasks is going to be horrendous when you try to parallelize using CPU. So we have to parallelize more intelligently so that we don't transfer too much data during the parallelization process between these tasks. And of course, that's a development in algorithm that people have been doing, and it has also made tremendous progress. So GPU is not the only way. Then we also want to speed up computation. And matrix multiplication or the dot product computation has a complexity of the order of n cube. If you take two entities which are size n by n, and I want to produce an output which is also n by n, then the order of complexity for this computation matrix multiplication is n cube. So basically in TPU, what they do is you take the basic convolution operation, and the basic convolution operation can be transformed into a matrix multiplication operation. And this matrix multiplication is accelerated using spatial processing like systolic array and etc. You also want to simplify the hardware, such as playing around with numerical accuracy. For example, when you do not training, but when you do classification, it turns out that we don't really need to do for image processing any more accurate calculation than just using simple 8 bits. In fact, and at least in some of the Facebook papers that I've described, they've gone down to like even 6 bits of computation. And so you don't really need to do 16 bits or 32-bit computation. So you just reduce the bit width, and that tremendously reduces the amount of the computation and energy. You also do, when you do that, you have to satisfy certain things such as expressiveness in terms of weights, expressiveness in terms of activation, expressiveness in terms of partial sums. When you do training, you also have to worry about gradients and weight update. So typically, it turns out that today the world has more or less standardized that on classification we use 8-bit data, and for training we use 16-bit floating point numbers. And this is not IEEE standard floating point number, but there's a floating point number called brain float or B float, and that's what basically most of the companies are using today. And B float is being supported by NVIDIA, Intel, AMD, and Qualcomm and others. So, and this is apart from supporting standard IEEE 32-bit floating point number and IEEE 16-bit floating point number. I might talk a little bit about the B float as we go through the presentation. And so these are some of the core acceleration opportunities for accelerating the kernel function for classification. For training, there are certain additional opportunities that you have for acceleration, such as doing faster convergence. There is no hardware approach towards that. These are purely algorithmic approaches. And so we can play around with things like step size and initialization, et cetera, so that we can converge on the model quickly. We have fewer iterations. And so in order to get fewer iterations, you must have good initialization. There's a whole bunch of research that goes on. Yes? So we use for classification 8-bit integer calculation. And for training, we use 16-bit floating point calculation. So for classification, the loss of accuracy is fairly minimal with respect to that. For training, there'll be significant loss of accuracy. So that's why for training, we use 16-bit floating point for training. But once the training process is done, then we have a model which are 16-bit floating point numbers. We then scale them into 8-bit integer numbers. There'll be small loss of accuracy, but that loss in accuracy is fairly small, and the trade-off is that you get tremendous amount of savings in power and computation, but at a very tiny cost to the accuracy. Yeah. And in training, we have different requirements than in classification. So in training, we have we must be able to express small gradients, which is why 16-bit IEEE floating point number has was not sufficient. And the way the brain float works is it has the 16 bits representation of the floating point number. The 1 bit is used for sign, and then 8 bits is used for exponent, 8 bits, and 7 bits are used for mantissa. And whereas in the IEEE floating point number, if you use IEEE 16-bit floating point number, then it will have 5-bit exponent and it'll have 10-bit mantissa. So what in BrainFloat is doing is it's increasing the number of exponent bits and reducing the number of other bits. And that's because you should be able to represent during the training process very small values, because we use very small gradient. And so when you have a gradient which has a value of 10 to the power, say, -5, okay, if you didn't have this many exponent bits, then this will just become 0. If you had 5 exponent bits and if you try to represent this number, then you'll approximate that number as 0. But if you had larger number of exponent bits, you'll be able to store this very small value. And it's very important to store, not lose the gradients which are very close to 0, because if you lose them, then during the training process, you'll be iterating too many times. And that will just increase the time to convergence. It will increase the amount of the computation, and training will be slow, and training power will be too large. And so it's very important that you're able to represent very small gradients during the training process. That's a restriction, which is why the brain float number was used. Of course, we could go into even bigger, and actually NVIDIA has a bigger number, and they call it TensorFloat, which nobody else uses. And so only NVIDIA has that, where they have even bigger number of exponent bits. Okay, so
because it's a 45-minute session, we'll take questions and then break for tea.
Sounds very good.
So any questions, please? I can get the mic. Yes, sir.
So is there any reason behind to choose the size of the filter, kernel filter? Because AlexNet is having 11x11, 7x7, 5x5. So then some other models are 3x3. Is there any specific reason behind that?
Okay, so there are 2 questions. Let me take one at a time. So the first question was, has BrainFloat been standardized? Yeah. So BrainFloat has become a de facto standard because every major company is supporting it. And anybody who wants to play a role in the training process, any architecture is supporting BrainFloat. Because as I mentioned, BrainFloat is used in training, not so in classification. So you can almost answer your own question: who wants to play in the training space? Does Intel want to play in the training space? Yes, they have BrainFloat. NVIDIA, yes, BrainFloat. Google invented BrainFloat, so of course they're using BrainFloat. And Microsoft was an interesting case because they came up with a number called MiniFloat, and that MiniFloat has something like 5 or 6 bit exponent and only a 2 or 3 bit mantissa. And they're using that in their FPGA hardware. And because in FPGA, if you want to do 16-bit operation, the number of cells that you'll end up using will explode. So they try to pack that into an 8-bit or 9-bit floating point number because they're using FPGA for computation. And then this was the famous catapult paper from Microsoft that described how they're using FPGA for accelerating their machine learning training and etc. And so that's the path that they chose. Of course, we have heard since then that Microsoft is designing its own hardware, but we don't know exactly what they're doing. But I suspect that BrainFloat is now being supported by almost everybody, AMD, Intel, NVIDIA. It doesn't have the standard IEEE certification, but it's standard.
Thank you.
Coming back to your question, I think I answered that partly when I was talking about the complexity, because if you use 11 by 11 or 7 by 7 filters, the amount of the computation is very large. And AlexNet used that because they also had correspondingly fewer number of layers. So the trade-off that people are making today is they have smaller filters, and with smaller filters, you get less accuracy, but then you can compensate that accuracy by increasing the number of layers. And as it turns out that when you do that, the total amount of computation actually decreases. If you have a big filter, it immediately blows up the amount of the computation. So when you go from 7 by 7 to 3 by 3, you reduce to your number of computations by a factor of 5. And even if you increase the number of layers in the convolution by a factor of 2, you're still ahead in the game because you still have a 2.5x savings. And that's why the trend is towards using smaller and smaller filters. This has tremendous implication on the decisions that people make in the hardware design. So for example, the tensor multiplication unit that Intel has put in the Sapphire Rapids, it has 16 rows and 64 columns. That would work well when the filter size is less than 16. When you multiply that. So that's like 4 by 4 filter. But if you do a 5 by 5 filter, then it would actually, you have to, during the convolution process, you have to tile that operation, you have to rewrite the loop slightly differently. So instead of fetching something just once and getting it done, you have to fetch it twice to get it done. And that's just, increases the number of memory fetch operation and the number of instructions you have to use. So it's intimately tied. If you're going to be using large filters, then you want to make your decisions in hardware design differently. And so I think today people have basically come to rely on the fact that this filter sizes are small and designing the hardware accordingly.
Any other questions?
Are there any studies like variable filter sizes? Like within an application, we can use variable size filters.
Of course, all the applications use filters of different sizes, but
I'm telling you, instead of only fixes like 5, 5, and 3, can they be 5, 5, and 3, 3 within the same?
Yeah, they can be. Yeah. So each filter can be different size. Each filter can be different size, and so if you can get away with small filters, then we don't want to use large filters. But sometimes that's not possible from the accuracy point of view. You can still use large filters, but it has an impact on the performance. So, yeah.
So whatever your computations you're doing, are the activation function, what are like sigmoid, are the computations included within the kernel computation?
Okay, so I mentioned that with AlexNet they use ReLU, and the main reason they went with ReLU and not doing sigmoid is because a sigmoid needs to call mathematical functions, which are floating point computations, and goes up too much. But in ReLU, it's just an if then else statement, which is just a subtraction. If the number is negative, less than 0, then the output is 0, else the output equal to input. And so that's basically just a test on the sign bit of a number. Is the sign bit set or sign bit not set? If the sign bit is set, then the output is equal to whatever is the rest of the field. Else, if the sign bit is negative, its output is 0. So it's really, really simple in hardware. I mean, when you implement that ReLU function in hardware. So that's why it is the most popular one. And even though leaky ReLU is going to do the job better than ReLU, ReLU is still popular because it takes so little to compute. Yeah.
Sir, one question. As you said, we can use number of filter sizes. Does the filter size depends upon the number of pixels we are focusing on the image?
Typically not. So typically we don't even work on the large pictures. So suppose we get a picture of high resolution, let's say 256 by 256, and in self-driving car application, for example. Self-driving car, we have a real-time requirement that given an input, we must be able to figure out, what are the things that we are looking at, and the perception must happen at a frame rate of, let's say, 15 to 20 frames per second, right? So we have put ourselves a limit that how much time each processing can take. So what happens is, I lost the train of thought. Can you repeat the question again?
Like I was asking, does the filter size depends upon the number of pixels of the image of the object?
No. So the first answer is no. And the second answer is the input size depends on the requirement. So for example, if I have a very high resolution camera, I'm not going to take my high resolution image in a self-driving car and trying to process that. I'm going to just subsample that image. And so I'm going to reduce my image size. And maybe I'll reduce my image size to something like 128 by 128 from this high resolution image. And I'm only going to process 128 by 128 input. So I'm not going to take a very high resolution image and trying to process that. Most of the time, it's a wastage of time because you do too much computation for too little gain.
No, I was asking not over the resolution of the image. I was asking the object in which if you're considering an image and it has an object, I wanted to identify that object using the CNN. So then the filter size will matters, I think so.
No, the object is made up of sub-objects. If you can recognize the sub-objects in the first convolution layer, and in the second object, if you can then see that how the sub-objects are connected, you recognize the object. So so ultimately it just comes down to very small filters.
Thank you.
I have a question about the iteration selection, and you mentioned about good initialization. I believe during training, if we are able to achieve good initializations as early as we can, we can train it much faster. And that even if the filter sizes are tuned, initialization is important. So are there any techniques that we use for identifying the weights depending upon the classific data set?
Yeah, there are a lot of work done on how to achieve quick and good initialization, and that would be another several lectures. So how to get initialization done? Yeah. So there's a lot of work that has happened on getting good initialization.
One last question, and then we'll take a break.
Okay.
Sir, in that leaky ReLU function, shall we take, is there scaling factor is only 0.1 or shall we take any other scaling factor?
You can take other scaling factors, but that one works pretty well.
Is it greater than 1 or is it exist in between 0.1 to 0.09, something like that?
It's less than 1, the multiplication factor.
Yeah.
And and people have experimented with various values. 0.1 works as good as anything else.
If I take the scaling factor equal to 1, what will happen to that network?
If you take that factor,
the scaling factor equal to 1 is the negative number and multiply with 1.
Then the leaky, then it's no longer. So remember that ReLU is this, and leaky ReLU is, if when you take 0.01 is this. If you turn that into 1, it's this.
Yeah.
And which is not a nonlinear function. It's just a linear mapping. So with a linear mapping, it would not work. Because with a linear mapping, even if you stack a whole bunch of convolution layer, it is equivalent to having just one layer. And so, again, I'm not going into the mathematics of that, but it's just, it will not help. So this number is usually 0.01.
Okay.
Yeah.
We have more than 2 hours of material to cover.
No, I think we are going fast. So I'll keep talking even faster.
Sir, one small doubt, sir. How the trained beef float 16 weights are converted to the integer 8 format, sir? Is it
Coming up?
Okay, sir. Thank you,
Yeah.
sir.
Yeah, please, sir.
Yeah, my question is, during the activation functions, you have discussed sigmoid and tanh and ReLU. Sigmoid and tanh seems to be in range-bound functions, but ReLU seems to be a non-range-bound. Does that make any difference in computations?
Not in the computational complexity, but it influences other things. And basically, it creates a necessity for normalization of the output. Yeah. And so I did not cover what a normalization is, because we all know what normalization is. If you have a bunch of numbers and they range from, they have arbitrary ranges, you want to squeeze them within normal range, then we just multiply them with some kind of a coefficient, right? So that's normalization. So ReLU needs normalization.
Okay, so when we are using sigmoid functions, is the data lost? In the ReLU, is not data is getting passed away. Like input is
No. So it turns out that if you use a sigmoid function or tanh function, then the number of iterations it takes to converge on a model during the model training process is significantly larger than if you use ReLU. So the whole purpose of choosing ReLU is to reduce the number of iterations it takes during the training process to converge.
Okay.
Any questions that? Yeah, then we'll take a break, and at 3:10 or 3:15 we'll start. Thank you. In mobile nets, we use depth-wise separable and point-wise separable. So actually, doesn't that the multiplications become same as those layers? I guess it becomes even much more intensive. So why mobile nets are used for mobile devices like embedded systems and so?
It's the total number of computations that's used. So if you do the total number of MAC calculation, multiply and accumulate calculation, then in mobile net, the total number of MAC operations is reduced. And that's just direct savings in power. Yeah. Muted it, just keep it locked. Yeah.
Small down. So actually, I'm doing a neural network model for DNA. So which is having this is a compression layer. This is the input layer, which contains 64 neurons. There I'm compressing it to some 6 neurons. So again, I'm converting back to 64. So I have trained this model with the ReLU function and leaky ReLU with that scaling factor equal to 0.5 at least. And after that, I multiplied the scaling factor 1. So where this with ReLU, I'm getting PSNR in terms of 30 dB, that reconstructed image. With leaky ReLU with 0.5, I'm getting around 31. When I use that scaling factor equal to 1, I'm getting good PSNR. Shall I consider this kind of network? Like if I use 0.5, that's still in the form of nonlinear only. If I take 1, so it will become whatever the values are getting here, this will be passed again. So it should be linear. Shall I train like that the model?
With linear, you don't need more than one layer. Because if you have more than one layer linear function, it compresses to just one layer.
Yeah. But suppose if I increase these output connections, so that here I didn't place any activation function, just some initialization function. Only here I'm using this particular one. Should I train that one? Is it valid kind of training that for image reconstruction? That kind of.
For one, no, it probably not.
Okay. So
Yeah.
the network contains only these two layers.
Yeah. Then
so
it's
that
okay.
Here I trained in 3 different ways.
Yeah.
In the first way, I tried with the ReLU function only, with the activation function. The second, I placed leaky ReLU with 0.5 scaling factor. After that, I trained with the 1, which means that the negative numbers also multiplied with 1.
Yeah.
Is that valid training only, right, sir? Why?
This is just known as linear classifier.
Oh, yeah.
It's no longer anything else.
I
It's
didn't
just
use any convolutions. Yes.
Yeah, so just a linear classifier. Yeah, just linear classifier. Yeah, so if you just use linear classifier with one layer, then this is as good as any.
Yes. If I wrote paper on that, they will accept like that, right? I'll make the discussion also in the paper.
Yeah.
So that people won't question like why have.
No, but people say that this is same as linear classifier.
But here, different kinds of some smoothing algorithms are there. So instead of that, it is that will take too much cost in hardware implementation.
Yeah.
So actually, I'm doing complexity sensing on neural network. So for that, in order to reduce that hardware reconstruction, I'm using only this neural network model.
Okay.
So in order to reduce that hardware cost, I'm using only one reconstruction layer here.
Okay.
So due to that reason, I trained the model with 3 different neural network, 3 activation functions. So with the first one, I'm getting lower PSNR. So when I use 0.5, I'm getting 31 kind of thing. If I use 1, I'm getting a little bit higher PSNR.
Yeah. That's just a linear network.
Yeah.
Yeah.
So that kind of reasons I can make and I can put it in the paper, right?
You put it, yeah.
In order to avoid the rejection after submitting the paper, that kind of thing.
Yeah. Yeah, I mean, that depends on the rest of what's there in the rest of the paper, yeah.
Actually, I'm going to implement it in the hardware on FPGA. So for that, I'm designing the lower weight.
Okay.
Lightweight version. Yes.
Yeah.
Is there any other algorithm other than backpropagation for training?
No, the backpropagation is the most efficient one. Any other algorithm would be, yeah.
I tried this plotting in the visual maps after the convolution layers with and without some faults, sir. And if I subtract, I get some features which are learned extra, sir. Is this method correct way of analyzing, sir?
Repeat again.
So this is the output of the convolution layers without fault, and this is with fault, sir. And if I subtract, these are the extra features, sir, which the neural network learned because of the fault, sir. If I can identify the number of faults, can I say the classification is classifying faulty? Like if it is,
yeah.
Yes, sir. If like 50% of the pixels value is faulty, then the classification will always go wrong. Something like this with the subtraction, can I work, sir? Subtraction of the visual maps.
It really very difficult to answer like that. So the thing is, whenever you're classifying, there's a classification boundary, right? The classification process inherently is tolerate some amount of noise, right? So whenever there's a fault, that is the same thing as introducing some amount of noise, right? Now, if the network was designed to tolerate higher amount of noise, then it's going to mask the effect of that fault. But if it had very low noise margin in the decision boundary, it's going to show too many faults when you do this difference, right? So it really goes back to the hyperparameters of the model, and so it's so that's why it's a difficult question to answer. Like if the model was very deep and very designed to tolerate large amount of noise, then maybe even with a fault,
Can classify correctly.
you can classify correctly. Yeah. So it's just maybe there's so much redundancy. Yeah. And so you cannot give like one line answer that it'll do it or it'll not do it. Yeah.
Okay, I can analyze with other models, then maybe.
Yeah, or you can design a different model which can still be able to tolerate that fault. So it's connected with the properties of the model rather than of the hardware.
Thank you.
Yeah. Yeah. Okay.
Folks, we are getting started. Please settle down.
Okay, so I will get started on the next item, which is basic CPU architecture and parallel processing. And I always like to start at the very basics, at the very beginning. And anyone who have taken the computer hardware organization class probably have seen this from Patterson and Hennessy, that there are 5 classic components of any computer, which is the CPU, and the CPU has data path. It has the control, and then there's memory, and then there are input-output devices. So if you look at the various companies in this architecture spectrum, where they're trying to accelerate, just as a quiz question, where do you think TPU is applied in this acceleration process in this figure? Yeah. In the data path, the answer is wrong. It's not dedicated memory in the processor. So think about in the Google data center, do they design their CPU? No. So they can't put the TPU anywhere here because they bought their CPU from either Intel or for AMD. So where are they going to put it?
Yeah, I think.
Let's go.
No, it's not shared on the Teams. You open the Teams, yeah. Same thing. Share screen.
It's showing there, so it's.
Instead of screen broadcast, can you? Presentation is not coming.
Screen broadcast. Yeah, I already broadcast the screen.
Can you stop and start?
Stop the broadcaster.
The screen.
Share PowerPoint.
No, it's only audio, so is it that way? What does this share screen audio means?
No, not this. It's share screen. Audio is turned off.
Yeah, share audio then. Share PowerPoint and
No. Share screen. And broadcast.
is visible there because we have connected the
Yeah.
port, but
Yeah.
it's not visible on the bridge for some reason.
Okay, let's do this. Let's end Teams and restart.
Takes it.
Hello?
Some mic is on. Some mic is on.
Yeah. But right now oh, I know. It's going through the HDMI port, the audio. And so, let's see. Right.
Same meeting, right? Same meeting. Just log చేసి break తర్వాత connect అవ్వట్లేదు. Sound here. Yeah, Teams also we need to mute. Stop that one. Present the now start.
No?
Hello, 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 hello. Hello, 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 hello.
Now check.
Okay.
It's also a touch screen.
Oh, I can still use this.
Yeah, you can still use the pointer at least. I think the stylus. Session was always okay, right?
Yeah, yeah.
It's very interactive. It's like Murphy. You plan for everything. Maybe you can take some questions.
Yeah, okay.
Meanwhile, if there are any questions, we'll take the questions. Please let us know.
We can go through Q&A while this thing is getting sorted out. The AV issues.
Generic question.
It's okay.
It's a generic question that I have. Will ChatGPT replace Google?
Uh, I think that they do different functions, so it's not.
That's different. Year on
The PF5 key will do it. Function 5. Where were you? Page number 45.
For PDF, it will not.
Oh, this PDF?
Yeah.
Control L. Yeah. Oh, this is not Acrobat. 45. 45.
Page 47.
47.
Yes.
So how many engineers will it need? We're going to try.
Page up.
Yeah.
Okay. Can I still write? No. You can't write. Okay, that's fine. Okay, so let's start the thing back, except I lost my ability to write, and so we'll just speak. So my question was that if you look for accelerator opportunities, where do you see the opportunities? So for example, if you do it in the data path, and that's where, let's say, the companies like Intel and AMD, they have full control over their CPU, so that's where they'll be doing some of the changes. That's not the only place, but that's where they'll be doing the changes. But if you look at a company like NVIDIA, of course, they don't do the CPU, and still the GPU has to connect to something. It's not a completely standalone device. So where will that be? It's not in the memory. It's actually one of the input-output devices. And so the graphics card, because the graphics card is input-output device, output device. And in this case, it's also an input device because you'll be able to read the data from there. And so that's where it's going to be. If you look at a company like Samsung, they're also into, they're doing acceleration in the storage space within the disk itself. There's a company called NGT Systems, and I'll show a slide from there. They're doing a hardware acceleration in their storage device for doing ML acceleration. And within the memory, now there's a lot of people talking about in-mem computing for doing the acceleration within the memory. And the choice sometimes comes down to necessity. Like, for example, if I'm not a CPU manufacturer and I want to do ML acceleration and I still want to play the game, I can't do it in the data path. So my choice will be somewhere else. My choice will be, like, for example, using FPGA for ML acceleration. How does the FPGA connect to the PC? So it connects to the PCIe slot. So I will then try to put my accelerator on the PCI slot. If I do it NVIDIA, I'll also do it in the PCI slot. If Google TPU is also plugged into the PCI slot. There are people who are doing accelerators on the USB. So it just goes in as a plug-in device on the USB where you want to accelerate. In each one of those cases, when they do the decisions, where they put it. So part of it is, what role they play in the industry. If I'm a hard disk manufacturer, like SSD manufacturer, I might want to put some of the ML accelerators in the SSD itself. And as I mentioned, that Samsung is doing that. Okay. And so obviously Samsung cannot put it in the CPU because that's a market controlled by Intel and AMD. And so that's like some of the business decision. Once you make the decision to go with it, it forces some choices on you. So for example, if you are connecting something through a PCIe, and let's take something like Google TPU, then it turns out that there's an overhead of sending the data from the, so the data is passed from the memory to the TPU. And so the first part of the process involves copying the data from the memory to the TPU's internal memory. The TPU also features its own DRAM. So copying it from the main DRAM to the DRAM which is in the TPU. And then once the computation is done, you transfer the result back, which is copy back. So just the two copy operations, it introduces huge amounts of latency. And so once you have large latency, how can you hide that latency in your computation is your number one consideration. And of course, when you are sending some computation to be done at some place and then getting the result back, you can't slice the computation small pieces at a time, because then the latency will clearly show. Because every little computation that you do is going to add that huge latency, and you're going to see that there's a huge overhead associated with it. So you'll have to parcel out computation in large chunks. And that's exactly what happens in GPU and TPU. The amount of the computation which is parceled out from the CPU to these devices, they're done in very large chunks. And the chunks is not there necessarily because that's how they want to do it, but because that's how they want to hide the latency. Okay, and it of course enforces some poor choices on them too, because if you're doing large quantum of data processing and with a large amount of memory transfer, the power consumption just goes through the roof. And so then they'll have to figure out, if people are worried about green computing, et cetera, which clearly everybody is headed towards, then how do they deal with that? And so it puts a handicap on that. If you connect with the USB, and Intel produces a part called Neural Stick 2, and which plugs into the USB port where it runs some kind of a hardware accelerator. I don't know if Intel will continue producing Neural Stick 3 or something like that, but for now, it forces choices in terms of, there is very, the latency is even larger than NVIDIA or going through the PCIe bus. And therefore, when you put something in the neural stick, you actually want to stick in a small embedded CPU in there, and which can just drive the process instead of the CPU being the main driver. So that forces some choices on you because you're sitting on the USB bus. And if you're similarly on the storage device, it again forces some choices on you. And so these are things that we'd like to understand that how these choices are being made. So let's just start with another very basic operation, which is how does the computation happen? We fetch something from the memory, and instruction from the memory. Then we decode the instruction, and then we fetch the operands from the memory. We execute, and then we store the result back into the memory. And then you get the next instruction. So there's a very simple operation. Think about it this way, that suppose I want to do my convolution operation, and for every convolution operation inside of the loop that you saw, I would like to fetch an instruction that says multiply these two operands. Then for that instruction, I need to fetch two operands, and then I need to fetch an instruction that says add the result back, and then I need to fetch whatever was the previous result. How many instructions I'm fetching per in that loop per cycle, and how much data am I fetching? So at a minimum inside of the loop, I'm fetching a multiply instruction, and I'm fetching an add instruction at a very minimum. So I'm fetching two instructions. Once I produce the result, I have to store it back. So I have another instruction to store the result back in many of these architectures. So I end up doing 3 instruction operations and then data operations. Each instruction operation, when you fetch from the memory, every memory read costs you power. Okay, and so if I keep fetching instructions this way, I'm not only spending power reading the data, which is a little bit of the useful activity, I'm also spending power reading instruction, which is an useless activity, because I need to operate on the data anyway. But all these instructions are an overhead in that case, because every time you have to just tell what to do. And so the choice that GPU makes, for example, is the programming paradigm is called SPMD, single program multiple data, in which you fetch one instruction which says multiply, and you're multiplying large number of data using the same instruction. So because it's the same instruction which is executing on multiple processing elements, and each processing element is doing multiplication on 2 pieces of data. And then you say add, every processing element is doing add. Then you say store, every processing element is doing store. How much instruction fetch have you shaved off because you're doing that? Okay, that just depends on the number of processing elements you have in parallel. By that factor, you reduce the number of instruction fetches that you're doing, which is real savings in terms of memory fetches, memory stores, memory operations, and that gives you performance, okay, and that gives you power. If you look at the same thing which is being done by systolic array, there are no instructions. There is basically a hardware unit where you put the data, and then every clock cycle you just simply cycle through, and every processing element does multiplication and accumulate, and I'll show you the hardware. There are no instruction fetches, and it's just simply clocking through, and it's doing the computation. And because there are no instruction fetches, and you do millions of operations, and you just not fetching. Actually, it's not millions; it's trillions of operations, and in the trillions of operations, you are not fetching like 3 trillion instructions. That's a tremendous amount of savings in power. So these are some of the choices that exist, and that's what we'd like to understand, how the architecture is influencing these things. So again, in the instruction set process design, we have architecture, which is the programmer's view. We have the implementation, which is the microarchitecture. Then we have the VLSI realization. And I'll just skip through that. So here is a very simplified view of what are the relative energy costs. So if you want to do, this for a very old technology like 28 nanometer technology. These numbers will be different now for 3 nanometers, but the relative numbers are not different. Okay, the relative numbers are all the same. So if you look at, if I want to do 8-bit add operation, it costs me 0.03 picojoules. If I do 32-bit add operation, it jumps up from 0.03 to 0.1. So that's like 3x, more than 3x kind of increase. If you do the same thing in floating point unit, then you see that it jumps up even further. But look at how much power it goes into SRAM read and how much power goes into DRAM read. What are the numbers? It's like 5 picojoules for SRAM read and 640 picojoules for DRAM read. So if you're doing this operation, what is one operation that you'd like to minimize when you're concerned about power and performance of doing this machine learning operation in the algorithm? It's basically reading from the DRAM. Okay, so if you want to, stop or reduce the number of DRAM fetches or DRAM stores, then we have to organize the computation in a way which is going to be called stationary. Just keyword is stationary. We fetch the data, and it's sitting in my cache, and I want to do as much as I can do with the data before I send it back to the memory. Okay, so it's not like when I'm doing the matrix multiplication, and unfortunately I lost this ability to draw. Suppose I have a big matrix, and I want to do an operation on that matrix. That matrix is an input matrix, let's say. So what I do is I fetch a part of the matrix, input matrix, and that would be called a tile. Because why am I fetching a tile and not fetching the whole matrix? Because that's all I can fit into my cache. Okay, I can't fit the entire input matrix into my cache. That's all I can fit. Once I fit the tile into the cache, I want to torture that cache as much as I can before I will write that, I'll fetch another tile. So what I'm doing is I have this big matrix, and I have this loop that goes from input index 0 to this last index. Instead, I've now rewritten the loop from index 0 up to the size of the tile, bring my data, keep doing operation on that tile, and then from that next index to that next index, fetch the next tile, and keep doing the operation. Is that clear? So what I'm doing is I've just rewritten my big convolution loop. Instead of working on the matrix, now it's working on a tile. And how am I choosing the tile size? I'm choosing the tile size by how much is going to fit within my cache. And how am I choosing my cache size then? So it again depends. Like if I'm in an edge device and I'm doing, if I'm in a CPU world, I already have the cache that I have. So I'm not doing anything special for neuromorphic computing, so that's my cache size is given. If I have an edge device, then I would like to have a very small amount of memory, because otherwise it's going to increase my chip area and the cost is going to increase, et cetera, et cetera. So there is this program called TinyML. And how many of you have heard of TinyML? And in TinyML, they're trying to compress the model size and try to bring in a tile which is small. And by small, I mean hundreds of bytes of the cache size, because I wouldn't want to have very large cache in an edge device. Okay, it doesn't make sense. It'll increase my cost. It'll increase my power. So first, I'm not doing operation. This is completely driven off this chart. As you can see, I don't want to do DRAM operation, and so I don't want to be dumb about my computation. I want to do one tile at a time, and the tile fits into my cache. And when I'm fetching from the cache, it's 5 picojoules instead of 640 picojoules, because an SRAM read. And I want to be finished with it before I fetch my next tile. So that's an operation. If you understand that, then it's fairly easy to understand that where will I be going with my computation next, because I want to be able to provide an hardware resource which can do this processing of the tile in one shot or several shots. So now let's imagine that I have a tile which has n pieces of data. Okay. And I cannot afford to have a hardware which can process all n pieces of data in parallel, because that will be too much hardware. So I want to choose something smaller, and I want to do it in multiple steps instead of one step. Would I choose n by 3 as a size, or n by 4? The number of elements I can process in parallel in the hardware. So if I choose my resource size as n by 2, I'll have to do 2 fetches, right? If I choose as n by 4, how many fetches will I have to do? 4 fetches. But if I choose some size in between, I'll still be doing 4 fetches, right? Because it doesn't fit exactly into that slot. So again, when I'm choosing my tile size, the tile size is coming from the cache or whatever memory that I'm going to do, and the chunk of the computation that I'm going to accelerate, that chunk size is going to be dictated by how many times I want to do. And so I want to do an integral number of fetches so that I'm not wasting any space in a fetch operation. Okay, every fetch operation is completely full, completely packed. I don't want to run my bus with 75% full, right? I want to want every seat occupied in the bus. Yeah. Yeah. So it's the cache is being used as a temporary store of the data, and so during the operation you keep going back to the cache and getting it instead of going back to the DRAM and getting it. The SRAM has very high reliability. We are not concerned about the reliability of SRAM. If SRAM has poor reliability, then we might as well exit the semiconductor business. Yeah. DRAM also has fairly decent reliability. Only when it comes to something like flash memory or resistive RAM or things like that, then we have limited reliability. We can do limited number of reads and writes, and typically about 100,000 writes that you can do.
We can all use SRAM.
There's a cost. There's a cost. Okay, so basically, you just I just wanted to give you how the high-level decisions may be made. And now this is another chart, which is computer system in practice, and this is going back to the days when I was working at Intel, and I left Intel like almost 19 years ago. Yeah.
Is not concluded. Can you just conclude that part? Number of cache size versus elements.
So I'm fetching a vector. I'm doing a vector operation. Now, my vector size is the size of the tile. Okay, and the tile size is the tile is a submatrix. It's not the whole matrix. So first, I chopped up my matrix into tiles. Okay, and so I'm going to do operation on one tile at a time. Then my tile is in the memory, in the cache or local memory, but I cannot put so many adders and multipliers to process the entire tile all at once because it'll be too many adders and too many multipliers. So I can only, in the hardware, do a portion of the tile. When I do a portion of the tile, that portion must be an integral subdivision of the whole tile. Because if it is not, then there'll be wasted time when I'm fetching only a part of the thing and I'm doing operation and they're going unused. Is that clear?
Tile being placed in the cache. Since cache is not in control of programmer, how can we make sure that tile is in the cache? Because cache can follow different policies.
So if you, I use the cache as a proxy for local storage. Okay, now if you're in the CPU world, in the general purpose processing world, and if you want to accelerate and also doing the same thing, doing some other operations, it's going to interfere with each other, right? So if you really care about acceleration, then all you're going to be doing is running ML jobs and not bother with running other jobs, right? Otherwise, there's going to be interference. But use that as a proxy, because even if I design some other form of accelerators, such as like in MIT, for example, they did this accelerator design called Iris, and which is some sort of a systolic array, and they bring in data from the memory, and then they just keep that memory around to do as many operations as they can. Okay, different organization. It's not quite cache, but it's just some local scratchpad memory. Yeah.
Sir, one doubt. So if I'm not processing the complete tile at once, why should I store complete tile in the cache? Can't I reduce the cache size also?
The reason you're storing the entire tile on the cache is because if you didn't store the tile, you'll have to keep refetching it from the DRAM.
Yes.
And so you're trying to reduce the number of DRAM fetches. And because the entire input cannot fit in your cache, you're bringing in a tile which corresponds to the size of the local scratchpad memory.
Okay, thank you.
Yeah. Okay, so that's, I'm just going by the very basic principles, like how you'd go about design. In the specific instance, for a specific problem that you're designing, you'll have all these constraints coming in, which will dictate what you're going to do. The next thing is, if you look at a computer system in practice, and this is a slide which is very old, when I was still with Intel, which is 19 years ago, and then it looked something like this. There's a Pentium 4 processor, then there was a system bus, and the system bus is also called FSB, or the front side bus. And then it went into a memory controller. And out in the memory controller, you see that it connects to the main memory, and then it connects to graphics output and gigabit Ethernet, and then you have the south bridge. So the memory controller is the north bridge. The south bridge was connecting to all these pieces of data. So if you look at this, then as I already mentioned, that where you would connect your accelerator, it really depends on what's your business. Like if you're Intel, you'll do in one way, or in AMD, you'll do one way, and others will do different ways. And that completely dictates the decisions that you make. And I'll show you an example of that. So the first order of thing that I want to do before I even try modifying my hardware is I want to exploit the parallelism opportunities that exist in that loop. So there are various types of parallelisms. One is called the data parallelism, that I can maybe do operations on multiple pieces of data at the same time. I can do task parallelism. Maybe I can execute different tasks in parallel. And when I do task parallelism, maybe I can do horizontal scaling, which is in some ways, which is what GPU does with task parallelism. But that's not the only way to parallelize tasks. I can also put it across multiple CPUs. And of course, there has been some efforts that I'm aware with at Intel, for example, with this, what is this thing called? The number of the number of threads that that Intel was doing to parallelize the the name of the chip escapes my mind right now, but let's just say that there's a way to do that. And we can also exploit algorithmic parallelism, and which is also what people try to do. We can also try to do instruction parallelism, executing multiple instructions in parallel. And of course, we can do SMT, simultaneous multi-threading. This is an opportunity that exists for parallelization. And these are opportunities that exist without doing, going into hardware accelerators. So let's just try to see how far we can go with parallelism. And there are different types of machines based on the type of parallelism that you're going to do. And so in the parallel computing world, there's this Flint's taxonomy that says that we have an instruction stream, which is the instructions that we're going to do, and we have a data stream, the data that you're going to process. And I can do instructions in parallel. So I'll have multiple instructions, and I can have multiple data. So accordingly, I end up with like 4 combinations. And I'll skip over. CSD is like the basic CPU architecture, which is your ARM processor, and which is the older single, Intel Atom processor. etc. Single instruction, single data. And then we have SIMD. And SIMD is very interesting because that's where a lot of the companies are focusing these days. We have single instruction and multiple data. What would be the benefit of having single instruction and multiple data? I just give an example. When you have this convolutional loop, inside of the loop, to do a multiply and an add, you have to fetch the multiply instruction, you have to fetch the add instruction, and you have to write it back. So there are 3 instructions involved. But if I fetched an fetched a multiply instruction, and if I could apply that on 100 pieces of data, then I reduce my instruction fetch by 100x, right? And that's the basic principle behind a SIMD operation. So let's look at how SIMD works. So for those of you who have taken a basic computer architecture course in MIPS, which is a very popular book, you know that there's a assembly instruction called add. And if you say R1, R2, R3, you're getting the data from register R2 and register R3, and then you're writing it into register R1. Simply replace that instruction add with add vec. And so I'm saying that do a vector addition, and now I'm no longer working on one piece of data, but I'm working on a vector of a fixed length. And in this particular example, suppose my vector V1 is 4 pieces of data, and vector V2 is 4 pieces of data. When I do vector addition, I will add 4.0 plus 4.5, I'll get 8.5, 3.0 plus 3.5, I'll get 6.5. So I'm doing all of them in one operation. How can I do that? So let us say that I have a 64-bit register. And how many 8 bits of data can I hold in a 64-bit register? 8 of them. So if I do an add vec instruction, then I can do 8 additions on 8 bits of data, where each data is 8 bits, that packed into 64 bits. That addition is different from adding 2 64-bit numbers, because with 2 64-bit numbers, the carry will just propagate all the way to the end. But when I'm doing vector, it's chunked up. It's 8 bits at a time. So this is going back almost 20 years. When Intel first introduced the SSE instruction, and then they went into SSE instructions, then they SSE2 instructions, then they went into AVX, and almost all the laptops that you use today, they will at least support AVX 256. So in AVX 256, there are 256-bit registers, and on the 256-bit registers, you can store data 8 bits at a time or 16 bits at a time in various chunk sizes, and you can do operations in parallel in that data stream. So almost all companies do that. And if you want to do a vector operation versus non-vector, how does it look like? So if I'm doing an operation where I just add vectors A and B, I may write a C program that looks something like this. For integer I equal to 0, I less than max, I plus plus, I do this operation. Now, when I convert it into assembly code, then the assembly code is going to look something like this. So for each addition instruction in the loop, how many instructions do I end up in assembly? 5 instructions in this code. But when I do add vec instruction, this is what it looks like. So instead of loading AI into register RA, I'm loading into register RA, but 4 pieces of data. And I'm loading 4 pieces of data into RB, and then I'm doing add vector operation, and I'm doing store. So I've reduced my number of instructions that I fetch from the memory by a factor of 4. And in real world, when you are programming, you can use the keyword restrict. And so, so in this loop, if you just put this extra command in the C program with Pragma IVTEP, which is what Intel compilers use, or Pragma OMP SIMD, and OMP is open multiprocessing, and this is what the whole world is using. Not specific to Intel architecture, but you can apply it across any number of architectures. And then if you write the loop, the compiler will automatically vectorize the code for you. Okay. And the compiler will automatically, in the Pragma, will take care of that. So instead of having simple add instructions, it'll do add vec instructions. If you buy, as I mentioned, that every laptop computer that you buy today has the AVX 256 implemented in it. If you're doing 8-bit operations, how much parallelism do you get? 256 divided by 8, which is 32. So you're able to do 32 operations in one instructions at a time. And on the desktop computers, we today have, like if you buy an i5 or i7 type of processor, they'll have AVX 512 instruction. So they have 512-bit register. And so now you're able to do 64 operations in parallel. And then going forward, that register length just keeps increasing. So all active processing elements execute the same instruction synchronously, but on different pieces of data. And so that's the basic idea behind SIMD. So let's just look at how Intel organized the old SSE instructions. The SSE had 128-bit registers, and for some of you, you're probably toddlers when the SSE was introduced. And so this is old already, 128 bits. But the memory could be organized as 2 doubles, or 16 bytes, or 8 16-bit shorts, or 4 32-bit integers. So there are many different types of vector operations that you could do. AVX 256, you have the data can be chunked up in this many ways, and that's giving you parallelism. And AVX 512 looks something like this. Either you can do 16 floating point operations in parallel, or 8 doubles in parallel, or 16 32-bit integers in parallel, and so on. So if you just provided a link here, if you click on this link, decoding the performance secret of world's most popular data science library, NumPy. So underneath the NumPy library, the mathematics is implemented using the vector instructions, and which is why, for those of you who use PyTorch, for example, and when you train, PyTorch calls the NumPy library, and the NumPy calls the SIMD code, and it's already vectorized, and that's giving you the performance. Okay, so that's the first thing that you're going to do is converting your basic loop operations into SIMD, reduce the number of instruction fetches tremendously, and at the same time, you're getting parallelization. And, so for example, with AVX 512, you're getting 64 operations in parallel, and at the same time, reducing the number of instruction fetches by 64x. So that's a tremendous savings. But it will not give you the savings if you did not tile your code. So if you're using AVX 512 instructions, how would you tile your code? When I take my matrix and subdivide, what should be an ideal division? And here I'm not talking about the cache. Let's just say that I'm going to do a small size tile. What would be the ideal tile size? So remember that in my register, if I'm able to fit the entire tile, that's perfect. So if I have AVX 512 and I can do 64 integers, so if I'm fetching one tile at a time, I'll be able to pack an entire tile of 8 by 8 into one register. And if I'm doing a dot product between two registers, it's one 8 by 8 tile with another 8 by 8 tile. And then I'm able to compute the dot product in one clock cycle and produce that output. Okay. So when I'm doing that, one of them is input, the other one is wait. Now, remember, if I'm filter size was 3 by 3, then with one filter, I'm packing 9 pieces of data. But my register can store 64 pieces of data. So what would be the best way to reorganize my computation? So I can do more than one filter at a time. So I can put the first filter here, the second filter there, the third filter there, until I have filled up the entire register, the 64 pieces of data. So when I fetch the data, and I've fetched one tile of data on my input, and I'm doing multiple filters in one cycle, and in one clock cycle, I'm able to do convolution on that input data against 64 divided by 9. Okay, so that's like 7. So I can do 7 filters at a time. Okay. If you didn't rewrite your basic convolution code to match with the architecture, the performance is going to look horrible. But when you speed it up with SIMD, typically people begin to see almost like 100x improvement in performance. And you may not get 100x improvement over NumPy or PyTorch because they're already taking advantage of the SIMD. But if you wrote your own code, and if you try to compare with NumPy, you will see that NumPy, the PyTorch is running 100x faster. And that's because people have really chunked up the data and optimized and tuned all this data movement and the computation. Next, we'll talk about MIMD. So here I have multiple instruction, multiple data, and MIMD is far more complex. Processors may be synchronous or asynchronous, and they have to be communicating. They can either communicate through shared memory, in which case I call them multiprocessors, or we could also do by message passing, in which we call them multi-computers. What would be the difference? So let us say that if you go to a data center today, and if you look at some of these latest AMD chips, like AMD Bergamo or AMD Milano, those code names that are going into the server processors, they, in one package, they feature 128 CPU cores, okay? And the 128 CPU cores, they share the same address space. When they share the same address space, each core could communicate with the other core just by going through the DRAM or by going through the cache. The last level cache, which is also known as LLC, they could just communicate, the two cores could pass data to each other through the LLC, for example. And in that scenario, you can get 128 parallel executions going all at the same time. So suppose I fetched a tile of data which is sitting in my LLC, the last level cache, and if I can just make the 128 things fire at the same time, I'm going to get 128x throughput, right? If you write stupid code, that's not going to happen. You really have to just finely tune that code to that architecture to get that thing going. But now imagine that I have one computer which has this 128, I can keep going. I have another computer, a separate, connected over the network, where I have another 128 processors. If I have to communicate between the two, then I have significantly larger communication latency. It doesn't mean that I cannot communicate. Remember, what is the trick to hiding latency? What would be the trick in hiding latency? Do a lot of work before you need to sync up. So imagine that there are two employees working in a group, and they share desks next to each other. They could be talking to each other, every hour, and as a result, they could do only tiny chunks of data work at a time, and they could just compare or synchronize. But if one worker is working in India, one worker is working in the US, and the internet connection is very slow, they will divide up the job. They'll say that you go from here to there, and I'll go from here to there, and only then we'll synchronize, right? So you are not doing fine-grained task partitioning, but you're doing a coarse-grained task partitioning so that you're trying to reduce the amount of the communication overhead, right? When you do coarse-grained task partitioning, then what you have to do is you have to copy large amounts of memory because you're not communicating too often, but you're working on your job. And while you're working on your job, you shouldn't have to go and ask the other guy, hey, I'm done. Can you give me some more data and I'll work on it, right? That cannot happen. So if you're going to be working longer, you will have to have your own memory, which is also correspondingly large, and so that you don't have to talk to each other, and you reduce the communication overhead. And when you do that, then you get performance. NVIDIA has very high communication latency when you go between the CPU and the GPU. If you look at NVIDIA RTX or something like that, how much local memory does that card have? 48 GB. Okay, so why do they provision 48 GB? Because you want to be able to just copy that data and go off and do your work and not need to just talk. And because that will add to the communication overhead. And when you're done, you've done a large chunk of work and then you communicate. What are you doing? You're hiding the latency of communication by minimizing the number of times you talk to each other. Okay, that's a latency hiding technique. If I'm doing any kind of MIMD computation, but there is going to be communication between the two, you will also have to hide the latency. And that means you have to go off and you cannot just take your loop and say that, I will do 2 iterations and you do 2 iterations, and then we exchange data and then we do 2 more iterations again. That cannot happen. So you have to say that, I'll do this layer, you do that layer. Or even bigger coarse grain, I'll do these 10 layers and you do those 10 layers, right? That's a very coarse grain kind of partitioning, parallelization. So what you're doing is you're taking this task and you're partitioning into the various granularity of activity. It can be fine grain, it can be coarse grain, it can be medium grain, and so you really have to pay attention to how you chunk up the task and you partition across so that you do this communication. So the message passing model, when you execute a job in a CPU, it's known as a process. And a process is defined by a program counter and an address space. A process may have multiple threads. Each thread will have a program counter and associated stacks, sharing the same address space. An MPI, which is the message passing interface, is for communication among processes which have separate address spaces. And so the parallel computing model can be, a data parallel, as we talked about Intel AVX, etc., which is SIMD, or it can be task parallel, which is MIMD, or multiple instruction, multiple data. And let's just see how it works, and by directly jumping into example. So if you take this program and if you compile it, you include this library in your program called mpi.h. And what it does is it includes the message passing framework into that model. And then you write your code and you first initialize the MPI in it. And then if you do this printf hello world and MPI finalize, the way you're going to run that code normally if it's not an MPI code, if you run it, you just call the program with GCC and you compile it and you produce a.out or whatever, and then you execute that a.out. In this case, you just say MPI CC minus O and you compile that and you produce a program called hello. And at the runtime, you just say MPI run minus number of processes. How many parallel processes will be executing that code? We just specify number of processes equal to 4. And then we say hello, and the 4 parallel processes will execute, and each one of them is printing hello world. So you'll end up with 4 hello worlds, okay? So we just created a parallel execution of the program, 4 of them executing at the same time. And so another example, suppose in MPI terminology, the process 0 is called the master. And suppose I write a program in which process 0 will send a message, hello, process 1, and or hello process 2, and then it will pass messages to 1, 2, 3, however many processes we are running. And process will reply back to process 0 is hello 0, process 5 is present and accounted for. Okay, so that's a simple message passing program that you're going to write. If you look at the MPI code, this is what it looks like. So you get the number of, when you run the program, as I showed you previously, that you specify the number of processes, and then you run this code. And this is one way we can easily parallelize that code. It looks very easy to do. MPI, it's not a difficult thing to write, but it's a difficult thing to tune. Because to tune, you have to know exactly what architecture you're going to run on, exactly how much communication to have in between the two. Because in this case, we have this communication primitives like MPI send, we are sending a buffer, and we specify the buffer size, which is the communication overhead. And this is what the code looks like. If I had more time, I would just go through each and every line of the code and I'll explain, but in this case, I'm just skipping that. So multiprocess versus multi-computers, again, just to recap, when the CPUs are sharing the same memory, then it's called a multiprocessor. And when they are sitting in different machines, it's called a multi-computer. And programmers must make explicit message passing calls in the code. And this is low-level programming. It has some disadvantages, but people who know how to do it, even without doing any sort of thing, by using, say, standard Intel data centers, by using a combination of SIMD and by using a combination of NPI, over running the code on a single processor, we can already get like 10,000x speed up in the machine learning training. Okay, this is just saying that do things better with the thing, whatever resources you already have, before asking for any sort of hardware acceleration. And because it's very easy to say that we need to accelerate everything in hardware, but the fact is that we already have tremendous acceleration potential and opportunity. We need to capitalize on that first before we basically start thinking about building new hardware. Okay, so with that, that is a very quick rundown of parallelization. I talked about data parallel, I talked about task parallel. And task parallel, I showed how to write code with MPI. I did not show how to write code with GPU. And if you're writing code with GPU, there are a number of things available to you. Similarly, you can use, if you use NVIDIA, you could use the CUDA environment, which is very well supported. But then there is also OpenCL. Any of you used OpenCL? Yeah, some of you have used OpenCL is heavily backed by Apple, and and also AMD. AMD actually backed something called OpenGL, Open Graphics Language, and Apple backed OpenCL, and so Apple, they have their own version of whatever the Mali GPU, which is integrated within the CPU environment. And so to enable programming that, they use that OpenCL. And it has similar primitives that allows you to parallelize and get performance. More recently, Apple started putting all this, in the M1, M2 kind of processors. They have started putting a very large number of processing elements for their GPU core, as well as for the neural processing core. And the real power of using that comes not from the fact that they have hardware, but they have the full programming support. And that with that full stack support, they're able to take advantage of the hardware. So it's not enough to just have the hardware, but it's also required to be able to use that hardware in a way so that every dumb programmer can write code and still get performance. Okay, I'm next going to talk about quantization and pruning. So, why do you want to quantize and why do you want to prune? And really, you do that to reduce, you do the pruning to reduce the model size, and you do quantization to reduce, simplify the computation. And again, the motivation for that comes down to the fact that your 8-bit operation takes far less energy, and 16-bit floating point takes far less energy than doing 32-bit floating point. And 8-bit integer takes far less energy than any other sort of computation. So again, I would like to reiterate, during training, we are using floating point, but during classification, we're using integer. So once the model is built, you have to convert the floating point weights into integer weights. And that's a mathematical step. So let's look at the basic idea, how floating point is scaled to an integer. So let us say that I have a weight matrix here, where the weight matrix has all floating point numbers, 0.97, 0.64, 0.74, 1, et cetera, and then it has that, right? So what I'm going to do is I'm going to take the highest value of the floating point, the red box, and the smallest value of the floating point, the green box, and I'm going to scale that into that integer. So how did I scale that into integer? I simply applied a scaling factor S of x, and so x here is a floating point number, and which could be 16-bit or 32-bit, and S of x is a floating point number, and then I'm converting that into an integer. So it becomes that matrix. So 1 is the largest value. And what is the largest 8-bit integer value? 255. So I'm mapping 1 to 255. And to do that, I divide by, the scaling factor is 1 divided by 255. So now we got an integer matrix. There is some loss of accuracy because if I revert back, if I take the original matrix W and do minus SW times W int, it's going to get this value. So it just shows that when I did the conversion from floating point to integer, I did lose a little bit of the value, but it turns out that that loss is so little that it actually doesn't change the classification accuracy too much. It does, and I can still recoup that by doing some kind of a retraining process. But let's just focus on that, scaling that number. So all my weight during training was trained as a floating point number. Then I converted everything into 8-bit integer. Okay. It turns out that after doing every convolution operation, we do normalization anyway. And so when you do this normalization, the multiplier SW that you're using here, that'll get dropped off. So when I do, so I don't need to convert it back into floating point. During the normalization process, all these multipliers SWs will simply get normalized and dropped off. So I can just continue to do computation with the 8-bit integers. So there are various types of conversions. There's symmetric, asymmetric, signed, unsigned, and so we could go through a lot of discussion, but I think we already captured the key idea, how to do this conversion. But people have tried different types of conversion to reduce the amount of the error in the computation, and it turns out that the one that I showed you, the simplest one, is used most frequently. Okay. So if I have an input X, and if I have weight W, and then I'm doing the multiplication, between X and W and then computing the output. As I mentioned to you that when I do the computation, we are not doing the entire matrix at a time, but only a tile at a time, okay? So let's just say that in this case, the tile can fit 4 Ws and 4 inputs. And this is my one possible hardware implementation where I can just multiply using this kind of a structure where each element is basically a multiply and accumulate unit. So I apply the weight and I keep shifting through, and then eventually I'll be able to produce this result over a period of 5 clock cycles, 4 shifts, and then producing the result. So this is a very simple hardware accelerator, and this might be simple, but this is almost at the core of all your mobile phone device. This accelerator is being used to do that. Okay, and there's a tremendous amount of software support for that. If I remember correctly, in the Qualcomm framework, for example, they create a file of this neural network model, which is called a DLC file. And in the DLC file, they already take the model, they chunk it up into tiles, and then they provide instructions as to how these tiles should be loaded and executed. So that on your mobile phone, when you're doing Hey Google or OK Google, that model is already downloaded to your phone, and with the instructions as to how to do tile by tile computation. I don't want to belabor this point because this is just getting into the weeds. It'll be like, I just want to keep everything at a fairly high level. Okay, so this is what I want to talk about next: post-training quantization versus quantization-aware training. So one way to do that training is I can just go ahead, find the weights, and then once I find the weights, then I'm going to do the quantization. Quantization is the process of converting the floating point numbers into integer numbers. And so I could do that, or I could, during the training process, I could already account for the fact that these numbers are going to be quantized at the end. And so my training process takes that into account and comes up with the weight vectors during the optimization process, which knowing that there's going to be quantization at the end. And it turns out that when you do quantization-aware training, then you end up with almost no loss of accuracy. And this is something which is already built into the tools like PyTorch or TensorFlow. You can just provide an option that quantize it for 8-bit numbers. It'll do quantization-aware training so that you'll have almost no loss of accuracy. And at the end, you'll be able to quantize the numbers. Okay, so we have basically covered quantization. And if I had more time, I'd go into more details. But for now, I think this is enough. I'll cover pruning, and I can take a few questions. So the basic idea behind pruning is that suppose we have trained this neural network. And after training the neural network, the edges indicates the weights, and the nodes indicates the activation map or the inputs. Okay. If the weight of an edge is close to 0, then I could just drop that edge because I know that it's not going to contribute too much, right? And at the same time, if there's a node whose input edges have all been dropped, then I could just simply drop that node. And when I drop that node, all its output edges are gone too, right? And so I can keep doing this process until I get a compact model. Okay. So what constitutes too small a weight? Like how close does it need to be 0? So basically the way people define pruning is like not by close to weights, but let's just say that prune 10% of the nodes. And then you find the threshold below which you will drop the edges. Okay, such that 10% of the edges will be gone, or 10% of the nodes will be gone. And you can safely prune 20, 30% of those things. And it's only when you are about 50%, then your accuracy begins to drop. Okay, so experimentally, people know that when you prune these networks, if you keep pruning, you don't really lose too much accuracy, and you start really losing accuracy after 30%, and around 50%, it just goes too high. Okay. The pruning is done after you have trained the model. You have the weights, and then you prune, and you get a smaller model, and then you use the model to do the computation. No, dropout is not quite the same as pruning. Okay, so let's say when you're training the network in PyTorch, and you use the pruning option, and you can say PyTorch that prune 10% of the 20% of the nodes, it'll produce an output model from PyTorch with 20% fewer computations than it would have produced without that option. So the model that it produces is already small. Okay. So that's so during the training process, you can already reduce the model size, and this is a built-in option. Okay. The very first time anybody tried that idea, it was actually Jan LeCun, and he wrote a paper and he gave it a funny title. He called it optimal brain damage. And, and because you're dropping those nodes and you're damaging the neural network, and he gave it a title called optimal brain damage. And since then, people have improved on that pruning technique. Now they don't do like the way Jan LeCun had done, but it's more like directly mapped into the loss function that you're doing during the optimization process. It's built into that. So how can I minimize the loss function while also reducing the number of nodes and edges? Okay, so maybe this is a good time. I can take some questions, and then I'll go into the TPU case study.
Hi, Professor. So regarding the pruning itself. So you just mentioned that one of the parameters that we consider is the loss function to prune. In addition to that, are there any thoughts on considering the hardware constraints such that, say, we have the net connectivity of the cores with a certain topology, and if we can actually consider the mapping of these tasks onto those cores in the order they have?
No. So during the pruning process, they are not thinking about where this model will be executing. They're just going ahead and in the PyTorch or in TensorFlow, the libraries that exist, they're not taking the architecture into consideration.
It's a general question. Like, do you think will there be any benefit if we consider architecture in addition to the loss function minimization or something?
So remember that if you do tiled operation, then pruning and tiling, they're not compatible, because when you do tile pruning, you're forcing some weights into zeros, because forcing weights into zeros is the same as dropping the edge, right? But if I'm doing that in a loop, and if I have a bunch of zeros, I can just simply skip through that operation. And so if I have a single instruction, single data stream computer, pruning really helps. But if I'm doing in Intel AVX or AMX instructions, it doesn't help, because I take this big matrix and then I need to chunk up the matrix into tiles. And so the fact that some values within the tile are zero is not allowing me to reshape the tile. Okay, and I'm doing tile-based computation. So pruning is not helping me in that particular scenario. So pruning really helps you when you're not doing the parallelization using vector operation, and when you're not, when you're basically working on an edge device or something like that, where things are very simple and not much vectorization.
Hello. Thank you for the presentation. I have two questions. Could you shed some light on how tiling affects the data flow and consequently the controller? And another question is, how do you know which aspect to exploit? For example, you have discussed about data parallelism, exploiting data parallelism, tags, instruction, or even like the pruning and everything. So how do you know which one to select or which like?
That again goes back to the core of where your business is and where you're trying to accelerate. Pruning is a great technique if you're in a low power edge device where you're not going to have vector processing. Okay, but if you're going to have vector processing like Intel processors, then pruning is not the right way to go. So because it doesn't work very well with tiling. So it really depends on the context, and some optimizations are applicable somewhere, but not everywhere.
And the effects of tiling on the data flow and hence the controller.
Yeah. It's a very good question. Effect of tiling on the data flow. So when you have tiled the matrix, then the question becomes, how will you fetch the tiles and do the computation, right? And so there is a way to fetch the tile and do the computation. So how you scan the tiles, you'll do the same computation, but you scan it differently. And that really depends on the exact implementation of the hardware accelerator that you're using. And so when I covered the TPU case study, it will that will be a good time to discuss that what impact tiling may have.
Thank you, sir.
So how are those dependency managed?
By the programmer.
On hardware level? Any logic or any specific hardware for that?
No, I mean, the hardware exposes the opportunities for parallelism, but managing the dependencies and managing all of that is dependent on the programmer. And so sometimes you can have very good hardware, which is completely underutilized, and you have really bad performance. And then some hero programmer comes along, and then suddenly everything works very well. Yeah. Okay, so I will then talk about the TPU case study. And first, you have to understand why Google went for TPU. And so basically what happened is they introduced TPU in 2016, okay? And at that time, they were just introducing all this voice command and everything. And imagine the problem of, let's say, IBM doing ML versus Google doing ML, okay? IBM doing ML, IBM does not have too many users, right, of their ML software. So there are, when people use Amazon, I want to train a machine learning model, so I don't want to invest in software, I don't want to invest in hardware. So I go into Amazon and I buy their cloud services and I buy their machine learning training software, which is SageMaker, and out comes a model, okay? And then I can deploy my model in my business or whatever. Okay, in that particular scenario, the effort is being spent in training, right? And so you want to, the acceleration for that training is Amazon's concern, how to do that efficiently and how to do that quickly. In Google's case, they have billions of users worldwide using their mobile phones. And if everybody starts saying, hey, Google, what's the temperature outside? And which, by the way, I do very often because where I live, temperature varies significantly. Sometimes there's a 30 degrees change in temperature in one day. And so I come into the office wearing shirt, and when I go out, it's freezing cold. And sometimes it goes the other way too. And so I frequently check while going out that do I need to put on my jacket or not. And so I say, hey, Google, what's the temperature outside? And it reliably responds. Now imagine if billions of users are doing the same thing. So what are they doing? What is their problem? The problem is that there are billions of users all doing classification, not training, all doing classification, even though classification by itself is low effort work. But when you multiply that with billions of users, it suddenly becomes a very high effort work, right? Because the workload becomes multiplied by billion. And I forget how many Android users are out there, but something like, I think, 3 or 4 billion Android users. That's very heavy. So what happened is, and a lot of people use translation services. Like, for example, if you travel and to a country where you don't speak the language, and it happened to me, for example, I was in Beijing for some time, and I wanted to get a haircut. And so I don't speak Chinese, and I went to the salon and I had my phone, and I spoke on the phone in English, and the Google translator translated it into Chinese and spoke it in Mandarin. Okay, so not perfect communication, but with the Google Translate app, I was able to get through. And I was able to get through with buying things, going to restaurants and everything, right? Now imagine if everybody starts using Google Translator app and there are billions of users, what will be their workload on the data center? It'll just be exploding. So around 2015 timeframe, they found that their machine learning workload was growing at doubling at a rate of like 3 months to 4 months or something like that. So imagine Moore's law is number of transistors at some point was doubling 18 months, doesn't happen anymore. But if you take the machine learning applications, and if the amount of the computational demand doubles every 3 months, you can't build a new data center every 3 months, right? That'll be way too expensive. So they were looking for a way to accelerate their machine learning work without doubling the number of data centers and massive capital investment on their data centers, right? It's a pure cost issue. And they are not CPU designers, so they can't go back and change the CPU. So what they decided to do is design this TPU and put it on the PCI bus on their existing data centers, and run all these consumer queries, the classification task, on their TPU, okay, which is sitting on the PCI bus. This is what it looked like. And so as you can see on the right-hand side is the PCIe connector. And then, it's a Gen 3 16-bit, a connection, the number of pins. And then on the top, you see the DRAM chips in this card. And on the bottom, you see the DRAM chips. And in between sits that TPU chip, the ASIC chip that they designed. Okay. And the goal of that was to accelerate some number of applications. So if you look at in the more recent things like Intel Z490 chipset, then basically the red dots are showing, where you could potentially accelerate. Like, so Intel is accelerating right in the core, in that red dot in the middle. But Google doesn't have access to that, so they are doing it on the on this. Yeah, so they're doing it on this PCIe. And people who do in-mem computing, they're accelerating here. But Google was accelerating there in the PCIe. So TPU is using 8-bit arithmetic. Again, why? Why not 16-bit floating point? It's classification. It's not training. And so they had this energy considerations. And around 2016, when they published their paper on the TPU, they basically said that the machine learning models that they're running for these various jobs that they have is multi-layer perceptron, one application. They didn't say exactly which application. They called it 0. Multi-layer perceptron 2. And then LSTM. This is like recurrent neural network, which is a variant of this CNN. And then LSTM, and then CNN 0, CNN 1. And so they're talking about the various computations that they do, how many layers they have. And so you look at how many fully connected layers, how many convolutional layers, and the type of nonlinear function that they needed to support. So this application was using ReLU. This application was using ReLU, but some of them are using sigmoid and tan H. And the total number of weights that you're looking at in that time frame, 2016 time frame, were already like of the order going up to 100 million or so. And then they're looking at the batch size, which is 200, 168, et cetera, et cetera. What's the batch size? Is the tile data, right, that they're working on. And so in terms of the architecture that they did, it's basically, they had this, the weights were coming through FIFO, first in, first out buffer. And then at the core of it was a matrix multiply unit, or MXU. And this is like the MXU. And the MXU was able to do 256 by 256 multiplication. That's the yellow shaded area. And to drive the MXU, you had the weights coming from here, and you had the data coming from there. You multiplied that, and then you accumulated. You applied the activation function, which is the nonlinear function. Then you normalize, and then you write the result back into here, and then you go again. So remember, one of the basic principles of operation is once you fetch a tile, you want to do as much on the tile as possible. So you write the result back, you keep processing that tile until you're done with exhausting all the operations that you can do, and then you go fetch again.
This tile classification is done part of processor, or the TPU itself will do?
It's done in the TPU. The classification is done in the TPU. So the processor is basically offloading, copying the inputs. It's coming from the PCIe bus, and then they copy the inputs into the DRAM. And then this is
local DRAM, I think.
Local DRAM in the TPU. And then the operation happens, and what goes back is the result. Okay, so the entire work is being done here. Only the inputs are copied, the weights are not copied. The reason the weights are not copied is because once you boot up the machine, it's running those 8 applications. All the weights for the 8 applications are preloaded. And so during the actual operation, you don't need to send the weights. The weights are already sitting in the local DRAM. You just need to send the input, and it'll get the weight from the local DRAM, and then it goes back. So in terms of instruction, you need to be able to say which application you're running. Like, is it application 1 or 2 or 3 or 4, so that it knows where to pull the data from, and so on. Right? So at the core, they have a matrix multiply unit, which is 256 by 256 multiply and accumulate unit, and can perform 8-bit multiply and adds. Again, that's a very large number. 256 by 256 is 64,000. Okay, why are they doing 64,000 processing at a time? To hide latency, and so the instructions that they have a small instruction set for the TPU, which is read host memory, read weights, matrix multiply, convolve, activate, etc., etc. And so if you look at the chip, the 24% of the area is in this matrix multiply unit with 64K max, and then they have control and accumulator. Interesting thing is that the multiplication happens with 8 bits, but the accumulation happens with 32 bits. Why? If you have a 256-bit vector, each element is 8 bits. When you multiply them, two 8-bit numbers, it becomes 16 bits. And then if you add large number of 16-bit numbers, then you cannot store it in 16 bits. There'll be overflow. So the accumulator is 32 bits. And that way you can take care of the overflow. This, by the way, is everybody does that, which is the input and the data widths are different, and the multiplier size is different, and the accumulator size is different. And so in CUDA programming, they already have data types where you can specify, what type of data you want to use, and people are always using different size for accumulator and different size for multiplication result and your inputs. So this is known as mixed precision computation, and again, when you're done with the computation and you go through the normalization step, everything is back into 8 bits. And what is that normalization? We just look through that it's multiplying with some kind of a constant, and that constant makes sure that everything just becomes a 8-bit number again. But in between, for some time, the numbers are 32 bits, then they again become 8 bits. No, the TPU is not SIMD model, so I'm just going to, so they have the matrix multiplication unit, and it actually falls like a systolic array paradigm. So I'll explain what a systolic array looks like. So this is the basic matrix multiplication loop, and if you have a 3x3 matrix, for example, you will write for I equal to, you will take a row of the first one. Oops. Now it starts like, I will take the first row and the first column, we'll multiply them together, and then we'll accumulate. So that's basically how it goes at a time for each element. It's a triple loop, and so it's an n-cube computation. And let's look at how systolic array is going to function. So I take the same computation A0, the same matrix A0, B0, etc., and I have, these are registers, and I put those values in these registers. These are shift registers. So the value A00 is sitting in this register, A01 sits here, A02 sits here, A10, A11, A12, and so as you can see, they're all displaced by one position in this alignment. So in the input data alignment, I first align the data into shift registers, and then I align the B matrix into shift registers where B00 goes here. Now I apply clock. So first, this element comes here, and that element comes here when I apply the clock. And this element moves there, right? And this element moves there. So it just shifts by one position. So in this unit, I'm multiplying these two numbers and adding with a local accumulator, which is initialized to 0. And then I keep clocking the system. And we can see what happens when you clock. So first, we multiply A0, B0. Next, what happens is B10 moves in from here, and A01 moves in here. So in the accumulator, this value is already sitting there, but now I take this value and that value, multiply them together, and add it back to the accumulator. So it has this result. In the meantime, A00 shifted here, and B01 shifted there. So I multiply them, and it's here in the clock cycle. So now I apply another clock, and it keeps going that way. And eventually, it just, when you have applied a 2n minus 1 number of clocks, the entire computation is going to finish. So that's the core of that matrix multiplication unit. It's called a systolic array. It's a good point to discuss that what are some of the elements. It would basically need staging buffer for shift register, and it needs data alignment, and then we need to kick off. Staging this memory is copy operation. takes time, more latency. And so you don't want to once you start shifting, you want to do substantial amount of work, and that's 256 by 256. Because if you only did like, 2 by 2, and you had to copy all that data, and then, which already took some number of clock cycles, then you just did only a little bit of the operation, you will feel the pinch that you didn't get much done in all those clock cycles. And so you're doing latency hiding by doing 256 by 256. The cost is tremendous, right? Because you got 64,000 multipliers and adders working in parallel. You could do 64,000 only because it is 8-bit integer. You could not do 64,000 if it was all 16-bit floating point. That power would be unsustainable, right? So we did that, and that kind of, I'm not spending more time on the TPU analysis. I think I've already explained that this is a design decision that Google made. First, they're trying to speed up only classification, not training. Second, that's why they did 8-bit. Second, they had limited set of applications. They could preload all the weights into that DDR3 memory that you saw, which is local to the TPU. Third, they were not concerned about security of the data. I didn't talk about security at all. If you're a general purpose computing company and selling the servers, then what will happen is one user may be doing the computation, but at the same time, that user may try to read what another user has stored in that as weights in that memory. So now you have to provide process isolation between the two processes. They didn't have to worry about that because it's all their own internal. So they didn't have to worry about process isolation and pay overhead for that. Like how does normally we do a process isolation? By using virtual memory. Every program has its own virtual address space, and then there's a page table that makes sure that nobody else can access another program's data. There is no such isolation here in this TPU. So if you take the TPU solution and if you say that apply in general purpose computing, it's going to add a whole bunch of overhead, which Google didn't have to deal with because they are their own users and they are not going to attack themselves. But in a general purpose computing in a data center, you can't do that because immediately people will try to attack and try to steal other programs' data. And so those are some of the decisions. So they had some advantages, some constraints, and they came up with that accelerator that they did. Okay. So all I'm trying to convey is that everybody's situation is different, and therefore everybody's hardware accelerator design is different. So that brings me to how are people then making these decisions? Well, there are many design metrics. You have to worry about accuracy or quality of the result. And some applications, I may not care so much about accuracy. Self-driving car, I care about accuracy, and I also don't care about accuracy. So this is how I don't care about accuracy. Suppose I'm processing my inputs, okay? In self-driving car, what happens is the entire program is roughly divided into two phases. One is called perception, the other is called planning. In the perception, you run your machine learning algorithm and you detect things that happens. And then in planning, you decide that what you're going to do, okay? So for example, supposing I have camera and I'm driving on a road and the camera is doing processing, let's say, 15 frames per second. I don't need to do 30 frames per second, but let's just say 15 frames per second. And in the first picture that I took, I classified that here's a car, here's a car, here's a car, here's a car, and there is a person, etc. In the second time frame, I do exactly that, but now I'm trying to do motion estimation. So is this car parked or is this car moving? And in the third frame, I will do the same thing, and I'll try to do motion estimation. And I'll say that, is this guy standing on the side of the road, smoking a cigarette, or is he trying to cross the road, right? So I have to do frame by frame tracking to do this object motion recognition. So in the process, what happens if I misclassify a pedestrian as a poster? And in the next time frame, I find that this object moved there. Then I already know that that's a pedestrian. So did I have to be super accurate in classifying a pedestrian versus poster? No, because I have redundant information when I go from one frame to the other frame. And because there is only limited displacement of that object, and I'm doing that motion tracking. And the first frame, even if I couldn't get a good view of this person, in the second frame, I might get a better view of the person. And because I have longitudinal data from this frame to that frame to that frame, even if I misclassify it here, but correctly classified there in the next one, I can go back and I know the story that I misclassified. So in that scenario, if you look at the algorithm has some fault tolerance built into it, because if I misclassify it, I still have a chance to recover. And so that allows me to lose some accuracy and simplify my model in some sense. And then I have a way to make up for it. So there's a clear a trade-off between accuracy and the amount of the computation. If I want to be super accurate, and it's not going to allow me to do real-time performance, then there's easy decision that lose some accuracy and get the real-time performance. Right? That's a direct trade-off. We have throughput, which is analytics on high-volume data. We have latency for interactive applications. You have energy and power that you care about. Your hardware cost, flexibility. And so what's flexibility? If I'm running, if I'm Tesla and I'm building a chip, I know that I'm running only on my sensor streams. And what are my sensors? I may have a ultrasound sensor, I have a radar, I have some camera sensors. Okay, and they're too cheap to put a lidar in there. But so I have limited set of sensors, and for each sensor, I'm doing this data processing. That's not an open and unlimited set of applications. If, on the other hand, a general purpose computing maker like Intel or AMD is designing things, they can't design it just for 4 applications, hardware optimized for 4 applications. They have to do it for 40,000 applications that other customers are running. That influences the decision. And so that's like the flexibility, the range of DNN models and the tasks that you're using. If you already know what are your tasks, it allows you to do a task algorithm hardware optimization, which I'm going to just quickly talk about. Scalability. So these are all the things. What are the key design goals? One design goal is reduce the number of multiply accumulate time per MAC operation, avoid unnecessary MAC operation, and if you increase the number of processing elements, we can do more MACs in parallel, and increase area density of the PE or area cost of the system. When you increase the number of PE, we have to think about the physical design. Can we lay out these PEs in a dense way? Can you get data into these PEs efficiently into the PEs and out of the PEs? Can I have a local scratchpad memory and just reduce the number of accesses? And so, how much latency can I tolerate? A low latency will just immediately put constraint on the batch size. If I want result very, very quickly, then you can't say that, okay, do this big batch and give me the answer in like microsecond. You can't do that. So these are all the trade-offs. So then you have framework to make decision how to do these trade-offs, and this is based on this slide is from VVNZ in MIT, and also combined with some input from Stanford. So the first is that in your workload that you're going to parallelize, there is some amount of available parallelism, and you cannot parallelize beyond that. That's the upper limit. But then if you think about the workload parallelism, you cannot really parallelize your workload completely because your memory, so suppose I need to do 10 tasks, and each task is going to require 10 pieces of data. So that means I need, first I need to have 10 processing elements, and then for each processing element, I need to get 10 pieces of data. That's going to require 100 pieces of data. In one clock cycle, I cannot read 100 pieces of data from my DRAM or from my cache. It's not going to support that. So how am I going to feed 100 pieces of data? I can't do that. And if I can't do that, then why am I going to have 10 processing elements working in parallel, right? So I'm going to reduce the number of elements up to the maximum memory bandwidth that I can support. And that already reduces to theoretical, the max data flow parallelism. And then we get down into the number of P's, we start making decision, etc. And what happens if you design a very large array, we might find that the amount of the data we fetch, we can only use this part of the array and we can't use the whole array because my memory bandwidth is not large enough. So how can I increase my memory bandwidth? What is the known way to increase my memory bandwidth? Think about a CPU. The DRAM is single ported. In one clock cycle, I can only do one read or one write. Then I go into the LLC. The data goes from the DRAM to the last level cache. In one clock cycle, in the last level cache, how many reads and writes I can do? It's just one. So how can I increase my LLC bandwidth? By banking it, by partitioning it, so that my last level cache is partitioned into, let's say, 8 blocks, so that I can do 8 reads or writes, right? And if I wanted to do 100 reads, I'll have to bank it by at least 128. And when I start banking by 128, and then I suddenly have real issue with the number of interconnects I'm going to have, and if they're all going to be in the chip, the amount of the layout and the routing complexity I'm going to have, I'll immediately have to start thinking about where to put these banks. They cannot be physically proximal, because if they're proximal, I won't be able to route all these wires. And at the same time, if I put them far apart, then they're going to cause problems too. So either way, I have to think about it. And so I have to think about what is the maximum memory bandwidth I can support, and what is the area cost I can support while making these decisions. And that's at the heart of this. So this model is called the roofline model. It's called the roofline model is because what happens is the maximum throughput I can get is the total number of processing elements I have times the frequency at which they will operate times the utilization factor. And ideally, my utilization factor would be 1, but in reality, when I'm going to write program, if I'm not able to use all the resources, then I'm losing utilization. It will be like 0.5, 0.6, and that's the maximum I could do. But in order to do that, I need huge memory bandwidth. But my memory bandwidth may be here. Okay, so as I increase my memory bandwidth, which is the bus width times the bus frequency times the utilization factor, then if I plot that, so in this part of the thing, it says I'm memory bandwidth limited, and I don't have enough memory bandwidth to support my computation. And here it's saying that I have caught up with my memory bandwidth, but now I'm processing element limited. So where is the sweet spot of operation? Right here in this corner. So we don't want to operate here. We don't want to operate there. We just want to always operate here. And that would be the ideal decision point in making accelerator design decisions. One of the other things that plays in a role in accelerator decisions is the data layout. And when I'm doing the data layout, for example, if this is my filter 2 by 2, and this is my input map, I'll place this filter here and I'll multiply, and then I'll produce that output. And then I'll slide this filter to the next, and I'll produce the next output. If I do that, then I can do the convolution, but I could also lay out my data this way, 1, 2, 3, 4 as a vector, and then the input I'm going to rewrite. And so remember, first time I'm going to do this 1 times this 1, this 2 times this 2, this 3 times this 4 times this 5. So I could just write it as 1, 2, 4, 5. So I can just simply have a matrix multiplication and produce that output. So what I'm doing is I'm taking my input and I'm changing my data layout. And sometimes the same data appears in more than one place. And I'm applying data transformation. And that transformation is really memory layout transformation. And the memory layout makes it easy for me to just fetch this, multiply, and get the result. And so that's very simple for hardware to do. If I didn't do the data layout, then in my regular hardware accelerator, I'm not going to have a smooth flow like this way or that way. I'll have to go like this, and that would be, not the best way to design. So basically, I have to do input processing on the data such that the data aligns correctly. And the second thing I want to do is I want to reuse the data in my accelerator as much as possible. So most programmers are not heroic, and that's why we have these libraries these are called BLAS, or Basic Linear Algebra Subroutine. And Intel, for example, provides its own subroutine library called Intel MKL, Math Kernel Library. And so Intel MKL will only work with Intel processors, but will not work with AMD processors, for example. For a similar reason, NVIDIA provides their own library called CUDA BLAS and CUDA DNN, et cetera, et cetera. And library will note the shape of the matrix multiply, select the implementation, do the data alignment, and all of that. So it's not just the hardware accelerator, but all the pieces need to be there. We do quantization and pruning, and then we do efficient network architectures. And this is where some of the questions were earlier in the day. So, for example, AlexNet, which was introduced in 2012, has 80.4% accuracy, 8 layers, and 61 million weights. And the total number of multiply and accumulate operations you need to do the computation is 724 million. MobileNet, which Google introduced in 2017, has classification accuracy of 89.5%, but it has 28 layers, only 4 million weights compared to 61 million weights, and 569 million MAC operations. So how did they go from 61 to 4M, with 61 million weights to 4 million weights? Is by choosing small filters, reusing some of the filters, and so on and so forth. So one of the things that they did is reduce the spatial size, reduce the number of channels, reduce the number of filters, and doing layer pooling. And so GoogleNet or Inception version 3, for example, did the following. So instead of storing a 5x5 filter, they actually store 2 vectors. One is a 5x1 and one is a 1x5, such that when you multiply those 2 vectors together, it becomes 5x5. But what does it do? How is it different from having a 5x5 matrix versus multiplying with 2 vectors? Can the weights be independent of each other when you multiply a 5x1 and 1x5? No, because how many independent variables are there? Just 10. And if I had a 5x5 filter, how many independent variables will I have? 25, right? So when I'm doing my training, I'm training just 10 parameters as opposed to 25 parameters. I'm going to lose some accuracy because of that. But at the same time, I make that up by having fewer computations and and fewer this. And so how do they do this multiplication? They actually apply them sequentially. So first do the convolution with the first one, 5 by 1, then do the convolution with the second one, 1 by 5, you're done. And so they're applying them sequentially. So it's like 2 operations, but each operation is very simple. Instead of 25, it's 5 and 5, 10. And so that's 2.5x savings. And yeah, they're going to lose some accuracy, but they're going to recoup the accuracy in different ways, which is just keep increasing the number of layers. And at the end, they make an engineering choice, which basically leads to that. VGG, which comes from University of Oxford, for example, they created a 5 by 5 filter as multiplying with 2 3 by 3 filters. And then, but each filter is moving not with a stride size of 1, but a stride size of 2. And so you see that corner, how they overlap, and it becomes a 5 by 5. Reduce the number of channels. So one way to do that is, like, for example, if I input at 64 channels, then I apply just a 1 by 1 filter, and that simply reduce the number of channels. And so GoogleNet, for example, did a whole bunch of 1 by 1 convolution, and a number of multiplications as a result reduced from 854 million to 358 million. And then there's also one way to do that is to split filters and channels into different groups. So basically, when I do a filter, I can do a filter which applies to only half of the channels and a different filter which applies to the other half of the channels. So instead of one filter going across all the channels, I can have 2 different filters, one working on half the channels, the other working on half the channels. And so at that point, this is pretty much becoming voodoo science as to how to split those channels and how to do those filters. And similarly for the, and some of these things like DenseNet, what they do is they try to apply the same filter in multiple layers. So if I used a filter in layer 1, I might want to reuse that filter in layer 5 so that I don't have to store the 2 filters. And so these are all various ad hoc approaches, and the layer pooling. I'm just going a little fast on this because I think I have to over the time. So just these are some of the ad hoc techniques that people use. And so the question is, how do you even think about how to split, where to split, et cetera, et cetera? The way they do that is not by any systematic way, but is just a brute force approach that says that let's just split this and try this way, and let's also split in a different way and try another way, and then see which one is doing better, and then I'll pick the better of the 2. And this is known as the NAS problem of the neural architecture search, in which you generate a large number of configurations, and then you train for each one of those configurations, which is computationally very expensive. But if you have the CPU power to burn, then you just do that, and then you come up with the best architecture, and then it looks like Google Mobile Net. It just it looks very ad hoc-ish. Like someplace they apply 2 filters, someplace 3 filters, someplace they do this vector, someplace they do actual filter. And it's completely looks ad hoc, and this is not something that you and I will be able to do using our compute resources. For that, you need like those, mega compute resources where you can run this network architecture search. And that's why when you go into PyTorch framework or something like that for image classification, there are only 32 network architectures people are using, and this is known as Model Zoo. So in that Model Zoo, there are only 32 architectures. Why aren't there more architectures? Because these are more efficient than anything else. And if you want to add a 33rd one, the amount of the network architecture search you have to do, like most people don't have that kind of computing resource. it's years of computing to come up with one architecture that works well. So there are many design considerations in co-design. One is impact on accuracy. And consider the quality of the DNN model, difficulty of the task in the data set, and sweep the curve of accuracy versus latency versus energy to see the full trade-off. Does hardware cost exceed benefits? And need extra hardware to support variable precision and shapes, and deal with sparsity, etc. Then does the programmer have the brain power and the willpower to experiment with the different granularity levels and what impact it will have on performance, which is serious consideration. And so these are some of the trade-offs, and time required to perform co-design, and training and fine-tuning, etc. And how does this approach perform on different platforms? And so if you come up with a solution that works for certain neural network models on certain platform, it does not mean it will work for other neural network models, or it does not mean that it will actually work in other platforms. So that's another consideration. So basically, if you're trying to come up with a method, you want to come up with a method that you can apply to a large class of problems, not just these 5 limited problems, or you want to apply so that I can carry the design for next 3 or 5 iterations of my design, not just I do design for this thing and then next year I do a different design. That it doesn't work like that, because software takes time to catch up. And so once you do something, then you have to stick with it for some time before the software had time to catch up. And these are all considerations in making decisions. Lastly, I will talk about the work that people do in memory and storage platform. And so trend is towards very large models and large amount of data movement. So if you're doing GPT-3, 170 billion parameters, I was completely off by a factor of 1,000 this morning when I say 170 million, so it's 175 billion parameters. And these are the various model sizes, like the popular ones. And so in data movement, where is the input coming from? It's coming from the sensors, and it's coming from the storage device. Like if you have the data stored in your SSD. And where are the weights stored? It's stored in DRAM, SRAM. And we try to make the reuse, but here is this company that's saying that the best place to do the machine learning acceleration is in your storage device, in your SSD. Because if you have a file stored in your computer, and if you're going to run classification on that, and it's going to have 175 billion parameters, the last thing you want to do is copy 175 billion parameters from the SSD to DRAM, then move that data to the SRAM, and then do the operation in the CPU, and read your input from the disk, and so on and so forth. So maybe we should just do it directly on the disk itself. And this company called, so think about an application. So suppose I have a 1 terabyte of SSD, which is nothing these days, it's only $60, 1 terabyte of SSD. And I have 1 terabyte of SSD full of images, okay? I want to search, give me all the images in this 1 terabyte of disk that matches Balpreet Singh, okay? So what would be my algorithm? Read one image at a time, bring it to the CPU, and then run the comparison, and then have the result. And then just keep going that. So if I have 1 terabyte of disk, I'd move 1 terabyte of data from my SSD to DRAM, and from my DRAM to SRAM, do the computation. It's huge amount of energy. So maybe we just don't want to do that. Maybe we want to do the processing in the SSD itself. And so in this company called NGT Systems, what they do is in the SSD, you have a bunch of flash memory. And the flash memory is like a number of flash memory chips, which are organized as channels. And so you have 16 flash memory channel. And then they do a custom design of ARM CPU, which sits inside of the SSD. So instead of ever moving the data from the SSD to DRAM, they are moving the search to the CPU, which is inside of the SSD. Okay, and then they do the acceleration inside of the SSD. So just the example that I gave will be done much better in that environment. And so here is some result from them, which is looking at the energy per frame of analysis. And these are some benchmarks, like for object tracking in video. So suppose you have a video which is stored in your SSD, and in your video, you want to track a person, and that appeared in a frame, which may be from 0.15 seconds to 0.25 seconds, and that person is no longer there, and then that person appears again in some other time, and you want to find that video segments where that person is actually there. And this may be a TV serial that has been recorded into a SSD, right? So how do you want to perform that? So in this particular case, when they do this kind of object tracking in the video, without transferring that, when they do it processing within that, then they find that for these applications, they are always the lowest energy level than trying to move it to the CPU or move it to GPU. So clearly for this particular application, it's doing in-storage computing and in-storage acceleration is going to be far more efficient than trying to do it in the CPU or any other kind of device. Samsung is also, there are two companies that I know of which are doing in-storage machine learning acceleration. So again, we talked about in storage, and this would be like somewhere here, the red dot, and then somewhere up there in the red dot is in-memory computing. So if you take one of your DRAM slots that you have on your system and then plug into the DRAM slot something which already has a machine learning accelerator, then what you can do is you can store the data in that DRAM, whatever DRAM exists in that slot. You have the data, and you just send a command saying that do these kinds of object detection or motion tracking, etc. It will do that in the memory slot and report it back. There are a number of companies which are doing in-memory computing. Already in-memory computing, IBM has accelerators, not necessarily for ML, but for database applications. And so for database applications, when they do encryption, decryption, most of the databases are actually encrypted because you don't want to give raw access. And so before use, you'll have to decrypt the data. And decryption is a very expensive operation when you have to just move the data from the DRAM to the SRAM, we do the decryption in the CPU, then write the data back. So instead, when they do search operation on decrypted data, they already just send the search query word to this memory. And the decryption engine actually sits inside of the memory and in the DRAM space. And then it does the decryption there, it does the comparison, and gets the result back.
People who came by bus, actually buses are leaving. They can avail that service.
So with that, I'm actually done.
So people,
Hey, thanks, Sandeep. Thanks for your energy and patience. Sorry for the glitches. Thanks. It's a nice presentation. And I know there are a lot of questions. Sorry for that. Maybe you can connect to Sandeep later. Thank you.
Thank you. Come to, come. This is for you. Thank you very much, sir. Thank you. Thank you. Thanks a lot. Very nice. excellent session. A lot of basics you covered. So much material you could cover in such a short time. Amazing.
Nice class, Sandeep. Thank you. I'm now working